Good afternoon. How are we doing this afternoon? Fantastic. Well, good afternoon and welcome to the 2025 UCLA Samueli Anniversary Celebration. My name is Jamal Madni, and it is my absolute honor to serve as your MC this afternoon. Today is a coronation celebrating two deeply special milestones. The first is the 80th anniversary of our treasured school being formed, and the second is the 25th anniversary of our school being named the Henry Samueli School of Engineering and Applied Science. Today's celebration is particularly meaningful and symbolic given the larger cultural context, as our beloved UCLA is in a fearless and unprecedented battle with those in Washington, D.C. And it is in that larger cultural context that I would love for us to look at the theme of today's celebration from the lens of an equation. And that equation is university innovation equals visionary investment plus unbridled brilliance. And for the sake of this audience, and in the spirit of all of us being engineers, I'm going to take the derivative of that equation. And the derivative of university innovation is societal impact. And so societal impact equals the rate of investment plus the rate of brilliance. And it is from that lens that we have curated a wonderfully meaningful program today for all of you that includes TED Talks, panel discussions, speaking, and recognizing the best and brightest Bruins across our ecosystem through our awards program. And so, without further ado, it is my honor to introduce our fearless leader, our Dean, Valerie and Ronald Sugar, Dean of the UCLA Samueli School, and also an individual that holds dual appointments in chemical and biomolecular engineering, as well as in civil and environmental engineering, the one and only Dean Alyssa Park.
Can you all hear me well? What a wonderful day already, and it's been really great to have all of you. First of all, Jamar, it's always nice to have you, someone who always helping us with events, because his energy and insight into engineering is always wonderful to see. And also his daughter, Zara, is celebrating her first birthday recently, right? Congratulations.
Thank you.
And we already made sure she has all the wardrobe of Bruin engineers, so I think she's on the right track. And welcome alumni, faculty, students, awardees, and sponsors and honored guests. Congratulate the 2025 UCLA Samueli awardees who will be announcing and celebrating soon. But more than anything, this is a really special day for all of us at UCLA Samueli. As Jamal mentioned, we are celebrating our 80th birthday. Oh my goodness, 1945 in August. I just checked up the number. 379 students started at UCLA Samueli. Amazing, right? That's 80 years old. This 80 years old ago, the students coming into, I don't know whether, do we have a Belter Hall at the time? Maybe, oh, we did, oh great. Them walking in, we had a really important mission. The public mission of empowering students and developing workforce for amazing engineering in the United States. And UCLA did that. UCLA Samueli did an amazing job producing so many great engineers, and many of them sitting right here. And I think the last 25 years has been really critical, but also very important. After Henry and Susan named our school 25 years ago with their generosity, we were able to not only become one of the global university educating amazing engineers, but we became the engineering school leading the global tech. starting from semiconductors, aerospace engineering, biotech, sustainability, and many more. I think our students are everywhere and making huge impact around the world and making societal impact. But this would not have happened over 80 years and 25 years, last 25 years, without our passion and joint effort and being there with each other. I'm so proud to say every single one of our students today, they know they belong here. And we are still celebrating more than 20% of our students, nearly 20% of our students are first-generation college students. The impact UCLA Samueli is making around the world is tremendous. And instead of me telling you our list of the amazing things we've been doing last few decades, we'll have a short video highlighting what amazing things happen at UCLA Samueli.
I grew up in Los Angeles, and after finishing high school, the only natural choice was UCLA. I finished my PhD in 1980. I went out to work in industry. The opportunity to come back and be a professor at your alma mater in one of the greatest universities in the world was too good to turn down. So it all was very synergistic. So it is quite remarkable how it has evolved over those 50 years since I started as a freshman to become one of the great universities and schools in the world. The growth, not only in faculty, but in students and in reputation, has been quite remarkable, and it's something I'm super proud of.
Nearly everything runs on computer chips these days. They make things go faster and more energy efficient. In the last 30 years, my research group at UCLA has been trying to make chip design easier and more accessible to everyone.
We are working on addressing grand challenges of the next generation microelectronic systems, which are able to think, sense, make decisions, and communicate autonomously.
Today, just 2 miles south of campus, UCLA's new research park is home to the Quantum Innovation Hub. It is where many engineering faculty will be bringing fundamental lab discoveries into transformative communications and sensing prototypes.
I'm an aerospace engineer. My research focuses on high-temperature gas dynamics using spectroscopy and optical sensors to study advanced rocket propulsion, planetary entry, and other reacting flows. At UCLA Samueli, our outstanding students gain hands-on experience through designing, building, and testing rockets and UAVs through the UCLA Rocket Project and other aerospace clubs. The students also benefit from strong industry partnerships, gaining internship and career opportunities in aeronautics and space engineering.
AI is changing the way we work, we live, and we learn. Since 2021, UCLA has partnered with Amazon to create the Science Hub for Humanity and Artificial Intelligence. It's the first of its kind for a public university.
As a roboticist, my research focuses on giving robots a sense of touch. I'm joined by a group of talented colleagues who are working on locomotion, bionic systems, robots for healthcare, foldable robots, and more. With the advancement of AI and machine learning, it opens up new ways for us to give robots the ability to perceive, learn, adapt, and make decisions. We are designing a more connected future, one robot at a time.
Leveraging advances in artificial intelligence, data science, machine learning, and genomics, we work closely with clinicians in the UCLA healthcare system to identify problems that can be addressed using artificial intelligence to solve these problems and transform patient care.
We're building personalized wearable health tech, precision imaging tools, artificial tissues, new immunoengineering therapeutics to tackle a range of diseases from cancer, autoimmune diseases to dementia. At the end of the day, our focus is what we can build and who we can help.
I'm an environmental engineer, and I study how everyday choices like what we eat impact the planet. We call it the carbon footprint with a D. At UCLA, engineers and computer scientists are building sustainable solutions from clean energy and mobility to carbon capture utilization and storage, as well as safer, more resilient infrastructure.
Earthquakes are among the most devastating of the natural hazards. We do work that characterizes the nature of those hazards. And we work with partners in the government and in the private sector to design more resilient infrastructure, both for earthquakes, wildfires, and other types of natural disasters that we face.
We have the tools and the responsibility to protect our planet for generations to come.
Our faculty members and students are brilliant. We are excited by curiosity-driven research and education. We ask tough questions and work together to find those solutions. This is the mission of public university, and I see this in action every day right here at UCLA Samueli. Dreaming something big is so much easier if we have shared commitment and goals. That is the spirit of UCLA Samueli.
I don't know about you, I'm getting goosebumps, don't you? It's so emotional, and this is our future and past coming together in a sense. As you can see, we kind of broke down the boundary of departments many years ago, and I think because we were able to do that effectively, all these 7.5 departments in Samueli Engineering, we are really tackling the grand challenge faced by humanity and tackling all these amazing scientific and engineering challenges, but thinking about the Earth and humanity within our system boundary. It has been really exciting leading this school for 2 years. As you may have heard, it's been a challenging year, actually challenging 2 years ever since I joined as the Dean of Engineering. But I think what I can tell you, and I hope that my students and faculty and staff can agree, that we didn't hold back. We are not holding back. We are moving forward, we're investing in our future, and we are dreaming big. And with that, we hired 34 new faculty members in 2 years. We're growing really fast, and amazing faculty members joining us. And finally, we were able to increase our undergrad admission by 10%. That's substantial, knowing that we don't have enough dorm rooms yet, but we'll get there. I think even having doubling our admit rate overnight, the quality of our students is not going to go down. We are one of the most applied to and most amazingly sought after university and School of Engineering in the world. So knowing that, we're just getting started. And I can't believe we're going to be doing this with all of you. And none of these will be possible without the support from our incredible donors and partners. Of course, Henry and Susan Samueli, thank you so much. And the Samueli Foundation, Lindsay is here with us. And we have RTX, Amazon, Boeing, CTS, Edison, Econ Instrumentation, HRL Labs, Northrop Grumman, PG&E, and many others. Thank you so much for all your support and partnership. And I thought, what would be the best way to start this amazing celebration and having a conversation with someone very important and everybody, the person everybody knows. So Henry, Dr. Henry Samueli, can you join us on the stage? Good to see you again, Henry.
Good to be here, Alyssa.
So I don't need to introduce him to you, right? I mean, you see his name everywhere and all that. And how many of you seen his footprints in front of Belter? Okay, how many of you try your own foot on that? Definitely, I'm way short compared to him. Who's bigger than him? I don't know. But it's really symbolic, the fact that your journey started in Belter Hall, and as you were walking in as an undergrad student. And looking back that time, you're walking into Belter Hall as a freshman. Did you ever imagine the journey you had?
No, not a clue. I mean, you can't. I was 16 years old at the time, so I was just thrilled to be coming to UCLA. I was just overwhelmed with the experience of being an undergraduate student at such an amazing university. So I didn't even begin to think about what's going to happen after I graduate, where I'm going to. I didn't even think about any of that. I was just worried about getting good grades in my next class. So you take it one step at a time, and good things happen.
So what was the most toughest class you ever took as an undergrad? What was the most difficult class you took?
Difficult?
Ah.
Good question. Probably wasn't engineering or math. It might have been philosophy or something like that. Because I loved engineering and math, so I took as many of those classes as I could and did very well in all of them. I was fortunate to be blessed to be good at those fields.
Mm-hmm. I should ask some of you that what was the most difficult class you took? Was it one of the Henry's class? We'll see. What did you carry with you from your early years at UCLA when you created the startup became Broadcom? Because at the time, it wasn't that common. Faculty members started a startup. Like, how did you even thinking about doing something like that?
Well, it actually wasn't any grand plan. I mean, it was almost like I was an accidental entrepreneur because we were just doing really interesting research here in the department, collaborative research with other faculty who are here in the audience today. Assad is here and others. So we built this great program in what we created called the Integrated Circuits and Systems Lab to do chip research for broadband communications and wireless and so forth. So the results, when we published them, were so interesting to the industry that they came to us and said, you need to start a company because we need these chips or derivatives of these chips for our products, and they don't exist. So please start a company. Literally, that's what happened, is they forced us to start the company, which we did. And we partnered with all these companies in the early days, so we didn't even need venture capital because they funded the R&D. So in the entire history of Broadcom, we never brought $1 of venture capital in because we had all these partners wanting to work with us to create technology for them. So it's just a fairy tale story.
Oh my goodness. Only if that's for all the story for all the startups, right? It kind of tells us that all the fundamental research you guys did in the ICSL lab kind of was relevant to real-world problems. And I think it's very visionary because although many of us working in the fundamental research, it's not often that question always comes from real-world problems. So obviously your colleagues and students and yourself had a very different point of view or different way of approaching the problem, maybe.
Correct. Well, I tell you, what really triggered all of that was the fact that after I finished my PhD, I went to work in industry for 5 years, and I went to work for TRW. Ron Sugar was my boss, I guess, back then.
Really?
And it was an amazing experience where I worked on military broadband communication systems for satellites and radios in the field for soldiers. So that's where I got exposed to the field of broadband and practical hands-on building of broadband systems. So when I came back to be a faculty member, that drove my research direction. It wasn't my PhD dissertation. I never opened my dissertation again post-graduation. That had nothing to do with the research I did. It was all based on my TRW experience. So I think hands-on practical experience really matters when you're trying to have an impact. And so those 5 years I spent at TRW, some of the best 5 years of my entire professional career.
That's great. As a person who did the undergrad, PhD, and faculty route, maybe I missed something big, not going into industry for a while. But did you ever imagine creating Broadcom? How it's going to impact everyone on the planet and more? I mean, I was just complaining to him that over the lunch that all the 500 plus emails I'm getting every day, maybe I should blame on the Broadcom. But did you ever imagine how it would impact the way everybody lives and connected with each other?
Not really. I mean, we knew the demand for broadband was there because when we started the company, you access the internet over voice band modems at 50 kilobits per second. So we knew that there was an insatiable demand for faster internet access. But we never really thought about what the breadth of all the applications were. The initial application was for digital television. So we worked with the cable TV companies on how to deploy these broadband modems to deliver digital television. But then it just exploded into social media and now AI. So that we didn't really anticipate the scope of the impact, but we knew that it was something important.
I think Broadcom and semiconductor industry had amazing, maybe last 30 years. And there's a renewed huge energy coming into semiconductor industry with all the growth in AI and more. I think as an engineering school, UCLA Samueli, it really shows not only Broadcom is important to you, but I think it's really critical and important for UCLA Samueli Engineering because the fact that not only we do amazing education and do research, the fact that one of our technologies, we claim ours, that became reality and changing people's life for better direction and empowering so many people. So thank you for creating amazing legacy in our school for sure.
And it was all built on the internet, which was invented here at UCLA, Len Weinrock's group and others. So, I mean, it's pretty profound that UCLA contributed to the invention of the internet as well as the invention of broadband and other amazing fields. So, very impactful what's going on here at UCLA.
I agree. We have a lot of faculty members and students following your footsteps. Of course, we want second and third and hundreds Henry Samueli in the future. But at the same time, I think the passion and desire for innovation stays with us and continuing. But also as a Dean of Engineering, as I was coming in, I remember I met you a little over maybe 2.5 years ago, right? When I was thinking about UCLA Samueli, whether I should join as a Dean of Engineering. One of the things I was really surprised that you were part of that whole process. I got to meet you even before we decided to move forward with my appointment. But I asked you a question, I think then, like, yeah, you graduate from this triple Bruin, but it is just a university and you can continue to give, and a lot of people do, but your generosity is far beyond just giving funding. It was so interesting during your busy schedule, you're meeting with our faculty and students and leadership over and over again and creating that vision together, and that really impressed me. And one of the many reasons, but one of the big reasons for me to say yes to lead UCLA Samueli was the sparkle in your eyes and go, yeah, this is a deep place, an amazing place. And I thought, well, I can do something. So why do you do what you do?
Well, I guess it's just part of my genetic makeup. It's, this place created everything that I have. So I am so grateful for my education, my faculty career. Nothing would have been possible at Broadcom without that. So it's automatic. When Susan and I created our foundation right after Broadcom went public, there was no question that this was the first major gift we would give because it's just the start of the payback and the thank you for creating everything that turned into Broadcom. And secondly, I enjoy it. I mean, it's a passion. I love engineering. It's not a job. It's a lifestyle. So I put everything I can into it here at UCLA. Now I'm chairman of Broadcom, so I do 10 times what a typical chairman would do. I don't just go to quarterly board meetings. I'm involved in meetings all the time and design reviews and business reviews because I love it. I'm just passionate about it. Just like I come here and serve on your advisory board, the Chancellor's advisory board. So it's just part of my life that I'm an engineer true and true.
I totally agree. And ever since I joined 2 years ago, he doesn't do just the serving on the board. He's there with me entire time. I think we talk at least every other month or something like that. And it's just amazing that what kind of big dream he has for our school. And he let me continue to dream with all of you for the future. And having that partnership has been really critical. And as you can see, we are continuing to grow and continue to empower people such a whole another level. But knowing we're engineering school, right? What do you see the future of a fast-moving technology area? What do you think UCLA and Samueli Engineering can contribute to future of tech and society?
Well, I don't think the innovation is going to stop. I mean, just like we've been innovating for 80 years, it's going to continue and hopefully accelerate. I think as we grow the school, as you continue to add faculty, we're going to continue to add more students. You're going to create a bigger and bigger research enterprise and teaching enterprise to train the next generation of engineers that are going to go out and found companies, work in companies, create new technologies. So I think it's going to accelerate over time, especially with the tools that we're now creating with AI. By using them intelligently, we are going to be able to do some amazing things in all fields, not just electrical engineering. It's now impacting everything both within engineering and outside of engineering. So our impact across the campus and across the country in all different fields is going to be felt immensely over the next few decades. So it's, to me, it's a time that's more exciting than I've ever seen in the history of technology. It's remarkable.
I agree. Well, 80th birthday, we'll have a 90th birthday and 100th birthday, I'm sure. And 100th birthday, we'll bring you back again.
My
of course,
pleasure.
we'll have many, many events along the way. But Susan,
I'll always be here by your side, Alyssa.
Exactly.
But you have to promise to be here too.
I know, it was really interesting. I was having a discussion with him and then I said, oh yeah, we want to do this, we want to do that, and keep getting bigger and bigger dreams. And I felt like there's endless. And then I looked at Henry and said, I actually said, Henry, am I crazy to dream this big? And he's like, no, keep going. And then, but he said, but you know, Alyssa, now you're hooked on long commitment. Like, how long? But I think it's a pleasure to be partnered in this dreaming big thing with all of you and having Henry and Susan being part of the family. We have a lot of exciting things happening. I think we have a vision of UCLA Samueli in 10, 20 years. And I think it's the beginning of another whole amazing era. And thank you so much, Henry, being part of the legacy. Thank you.
Thank you, Alyssa. Thank you.
Great.
Well, thanks so much again to Henry and Dean Park. What an amazing fireside chat that was. You know, a couple things that struck out to me. One is just how organic Henry's entrepreneurial journey was. And it was about the love of solving problems, about the love of advancing technology. And the outcomes came along the way. And so it's such a lesson for all of us that sometimes it's better to be process-oriented than necessarily outcome-oriented. And so that was really terrific, Henry, a really inspirational conversation. Well, as we segue into our program, it can't be a celebration without recognition. And so very, very excited to have our first two awards presented here in the form of our Excellence in Teaching Awards. You know, UCLA is such a special place. We have three fundamental pillars: research, teaching, and service. And all three are so fundamentally important and intertwined to one another. And the lifeblood, in many ways, is teaching. And so I am truly honored to recognize two professors that I think really epitomize the term multidisciplinary. And especially as we go into this world where the boundaries of the traditional disciplines are blurring so much, that these two individuals are really shining examples of being inspirations in the classroom. And so the first individual that I am honored to highlight is the Eon Instrumentation Excellence and Teaching Award winner, and that would be Professor Sriram Sankararaman, who was a professor of computer science, human genetics, and computational medicine. So Professor Sankararam, I would love to bring you on stage, along with Dean Park.
All right. So very quickly, I'm truly honored and grateful for this award. Of course, there are many people to thank, but I'm going to keep it brief. Firstly, I'd like to thank my own teachers, who have been a big source of inspiration on my journey to continue to teach and educate. I'd like to thank my department for supporting me as a junior faculty and continuing to support me as a more senior faculty now. And finally, my students, and many of whom have TA'd my class, who've often gone above and beyond what is needed, who've been a constant source of energy, inspiration for me to continue to teach. And I hope to continue to teach, educate, and serve this wonderful student body that we have. Thank you.
Thank you so much, Professor. And our second teaching award that we're so excited to present, the Northrop Grumman Excellence in Teaching Award to Professor Tyler Kleitz, who was a professor of mechanical and aerospace engineering, as well as bioengineering, a Forbes 30 Under 30 recipient in 2018, and someone who was just extremely distinguished both inside and outside the classroom. Professor Kleitz.
Thank you. You know, it's a really special award for me. I care deeply about the students that I teach, and I work really hard to try to prepare them for a future in engineering and careers that will really, truly change the world. And so it's deeply meaningful to me to be nominated for and to receive this award that focuses on that teaching and recognizes that. I'd like to thank those in my department who nominated me for the award, Professor Jonathan Hopkins, Professor Jeff Carman, Professor Greg Carman, Professor Jeff Eldridge, all of whom were extremely have served different roles in mentoring me and guiding me along the way in that teaching journey. I'd really like to thank the other people in the department who have guided me and mentored me. I'm grateful to live and teach in a place where we have the freedom to teach truths and to teach to students in ways that will really truly benefit them. And lastly, I'm grateful to my family, my wife, who's a sounding board for both ideas and challenges, and my kids, who epitomize the curiosity that I think drives classroom learning, but also teach me some of the patience that I need to be a professor as well. So thank you very much.
Thank you so much, Professor. And we're just keeping the program moving along. So now we have our first panel. Very excited about this discussion, the future of healthcare, from a number of different perspectives. And I think the panelists and the moderators are just absolute powerhouses. So I'd love to invite at this point Professor Kleitz, Professor DiCarlo, and Professor Markovich onto the stand here. as well as our moderator, our esteemed Associate Dean of Research and Physical Resources of the Samueli School, as well as joint appointments in both the ECE department as well as the Mechanical and Aerospace and Engineering department, Professor Rob Candler. And we're really excited about this discussion.
All right, welcome everybody. Again, I'm Rob Candler. I'm really excited to host or to moderate this panel discussion on the future of healthcare. I think the main reason I'm excited is because we have three really interesting and engaging colleagues that we get to talk with today. It's a big question to ask, so what we're going to do is I'm going to let everybody have a brief introduction, and then we'll start off with a little appetizer question, and then we'll broaden it out a little bit. So maybe we could start with Dino and back this way, if you could give a brief introduction.
Hello, I'm Dino DiCarlo. I'm a professor of bioengineering and chair of the bioengineering department. I started at the Samueli School of Engineering in 2008, so I've been here 17 years. And I think have that also that drive to have translational impact in our work. And so we've invented a number of technologies and translated those technologies, including a test for sepsis that's now being used in hospitals across the U.S. So, pleasure to be part of this community.
I'm Tyler Kleitz. I'm an assistant professor in mechanical and aerospace engineering. I have joint appointments in bioengineering in the Department of Orthopedic Surgery at the medical school. My research focuses on bionic systems for augmentation and rehabilitation of human movement ability. So we think a lot about how people move, how they may lose the ability to move, and how we can restore that ability to them. Our work bridges prosthetic devices, orthopedic implants, and into wearable assistive devices or devices that may even someday augment human performance. So really excited to be here and to talk about the future of healthcare.
Hello, I'm Dejan Markovic from Electrical and Computer Engineering. I joined UCLA in 2006, so this is my 20th year. I had a blast, a lot of really interesting projects over time. I was trained in semiconductors and chip design, but I also recognize enormous opportunity here to engage with medical school. So I have a sort of a dual career, maybe 3 careers if I wrap in kids, but for my professional career, I would say I still develop runtime reconfigurable processor technology for building hardware accelerators on the fly. Which is a really fast-moving and highly impactful segment. And I also have really genuine interest and work in medical devices, clinical research systems. And about 10 years ago, I did 2 really kind of a parallel track projects, one that resulted in embedded FPGA technology, which transitioned last year to analog devices, and another one, which was more like a hobby project, but solved a really interesting problem, getting EEG waveforms and turning them into an intuitive computer music for seizure detection. And so that also transitioned into Cerebell, which became public last year, and now is used in more than 500 hospitals and growing. So that's kind of really what drives my research interests and keeping those dual track opportunities, really a lot of interesting things to do.
All right, so as you can see, we have a super interesting breadth between cell therapy, assisted devices, and neural interfaces. And so one question I thought would be really interesting to start with is to hear what you all think about how we might treat spinal cord injuries in the next, say, 15 to 20 years. So if you're my generation, your Superman was Christopher Reeves. And 30 years ago, he had an accident on a horse, and he had a spinal injury, and he really never recovered from it. And so, at that point, I'm thinking, if we can't help Superman, what hope do we have? And so things have changed quite a bit already in the past 30 years, and I'm really interested in kind of what you think about how we might treat them now, and then how we might treat them in 20 years from each of your kind of technological lenses.
I can start from kind of a cell engineering perspective. So I think many of the bioengineers that we have here are interested in how do we use biology to solve problems? How do we understand the language of cells? You think about regeneration as something that actually happens in nature, right? You have axolotls, you have other animals that can regenerate tissue. They have particular cells that communicate in ways that instead of creating scar, they form new tissue. And we're just starting now to understand that language between cells. So I think that there's maybe in the early, in the short term, we can have some potential approaches where we put whole new cells into these spinal cord injuries and hope that they will form some connections that were blocked. These would be like stem cells, neural progenitor cells. But I think in the long term, and this is also driven by, I think, use of AI tools to understand the nature of cell-cell communication. Biology is complicated. Cells produce thousands of different secreted molecules. They have thousands of different cell surface molecules, and they interact with each other. And there's this melody of how they interact, this symphony of interaction that we really don't understand. And so, where we see a big impact is if we can start to understand those conversations at scale using AI tools as well to make predictive foundation models of cell-cell communication, not just human language, that can allow us to intervene to create connections, these neural connections where they weren't before, to create the surrounding supporting tissues where they weren't before, and to reprogram the environment to be in a regenerative environment where now you have full connection that allows range of movement for these spinal cord injury patients. So I think it's an exciting future. We're not there yet with engineering biology, but I think leveraging tools, we're going to get there soon.
Oh, Dino, that's beautiful. It also sounds really hard. So I build robots. I like things that are big. I tell my students I don't really mess with anything smaller than a nerve. So I think our perspective is a little bit different. I think that is a future that is definitely one that I think, once we do that, then my whole career is fairly obsolete at that point. But fortunately, that's maybe not but that's a little ways off. So the way I would say that we can think of this in kind of the near term and then the far term is, when someone loses, when someone has a spinal cord injury, what you're losing is a connection, right? You're losing a series of connections that bridge from one kind of level of spinal control and neural control to another level of spinal and neural control. We want to do our best to bridge that using the technologies that we have available to us now. So if that's robotics, then sort of one concept there is that you read and interpret electrically what someone is trying to do at a level where you can, maybe a higher in the spinal cord or in the brain above that level. And then you replay that information on a robotic system down below where the injury happened, right? So rather than regenerating the natural spinal cord, you're sort of building an artificial spinal cord. I work a lot in the legs, and one of the cool things about the legs is our legs actually do a lot of movement, a lot of processing, without our brain knowing a ton of it or really participating in it, right? Our brain can modulate it, can change it, but a lot of that processing actually happens in the spinal cord and even in parts of the spinal cord that might be sort of below that area of the lesion. So one of the things that's cool that we can do is we can build robots that mimic the behavior of the spinal cord and just take a little bit of input from kind of across where that injury is, but they sort of think on their own, right? So we've all seen, I imagine most of us have seen the humanoid robots that are walking around. Many of them walk in ways that are starting to look more and more human-like. So if we can take that and replay that on a wearable robot and have it be the person's limbs that are moving instead of the robot's limbs that are moving, we can start to leverage some of the things we've learned about how to make the robot adapt to different terrains and walk up and down stairs and things that look from the outside like real objective decision making, but really are driven by these sort of simple rules about how that robot is interacting with the world. And we can replay that then on a person's legs and have a person walk. If we take that one step further, the other thing we can start to think about is instead of rebuilding their function using wearable devices, we can start to rebuild their function using their own muscles. Right? So if we take that same concept of replaying the behaviors that we expect that they're trying to do, but do it instead by stimulating their muscles, now we get to a form factor where the person doesn't actually have to wear a bulky robotic system, and it's their own muscles that are doing the movement. All we've done is we've replaced sort of the central processing chip that was above the level of the spinal cord injury. We've replaced that with something synthetic and computational, and now we're just interacting with their spinal cord in a new way. I'm going to cut it there.
All right, so this was a really great segue, and I do think this is a multifactorial problem. For anything that relates to medical applications or just any real-world applications, I like to say that everything starts and ends in the clinic. So looking how to serve the needs of clinicians and stakeholders that are patient-centric is really important. And I see clearly three phases of technological intervention and assistance in this particular space. Number one is dealing with the acute injury and applying tissue scaffolding and growth, as Dino mentioned. The second one I see also engaging retraining of the altered state of the central nervous system and brain control coming down into the through the neuromuscular system. And that's where I see a great intercept of the modern brain-computer interface technology and data analytics going into the future. And of course, that has to be done very carefully in a closed-loop manner because brain and our body adapts as well. So we need to kind of devise really carefully closed-loop feedback and treatments to do that. And the third step, which overlaps partially, but the second one is exoskeleton and assistive robotic technology that would aid in therapeutic recovery and rehabilitation phase. Maybe not to the level of fine motor control to get a perfect golf swing of Tiger Woods, but certainly you would be able to restore as much of that natural rhythm and retraining, again, central nervous system and redeveloping that muscle memory with everything that's happened. So kind of really breaking it down to electrochemical processes that occur at the fine grain, dealing with the medication, tissue scaffolding, and tissue engineering, as well as technological aspect and doing neurostimulation.
I'm wondering if, oh, go ahead.
I was just saying, we're aiming for Tiger Woods. We're trying to get that golf swing back.
We're going to loop back to that in a little bit, but I'm curious if what your thoughts on either yours or the other technologies, what do you think is the most, I guess, daunting or important challenge that you don't know how to solve yet that's preventing us? And is it, for example, neural interfaces, does it have to do with persistent biofouling or things like that? So I'm curious kind of what you each think about that.
I'll start with engineering biology. I think the approaches taken so far have been putting cells that look like the cells that form these connections, neural progenitor cells, into a damaged tissue and hoping that they'll form connections. And so that, that's not necessarily engineering, right? That's, you're saying, if we take apart a system and we put parts of it back, that we hope that it will form that system again. But if you think about what really happens and how we create our spinal cord, it occurs as embryos, right? As tissue, during tissue morphogenesis, right? So as tissue kind of cells grow, they divide, they fold, they're talking to each other as they form these new tissues. So it's not that if I just took all the cells apart and put them back together, they're not going to form your body again. So I think that's been one of the big challenges, is that we have now tools that we can kind of catalog all the cell types in the body. And that's been pretty amazing. Like, over the last decade or so, we can catalog very precisely. We have X amount of cells in the body. I think it's it's in the different types. There's thousands of different types. But we don't know how to create connections between those cells, how to direct their formation of tissue structures. And so we're kind of at the stage of we have these blueprints. You know, the analogy I like to use is, you know, we have the instruments that are part of the symphony, but these cells are communicating. They're riffing off of each other in these melodies. We don't understand those melodies. And that's really the music of life that's going to allow us to create these, you know, the tissues that we need in order to regenerate and form, you know, multicellular kind of constructs that are important for something like spinal cord injury. So I think that's the gap, is not, you know, we have a catalog, but we don't have those connections. I think that's an area that we can build data, and we can start to then have truly engineered kind of therapeutic options.
In my space, we think a lot about interfaces, because we're trying to build machines that interface with the body. And there are obviously in this problem, there are biological interfaces, there are electrical interfaces. I'm going to focus on one that we don't actually think about a ton, which is the mechanical interfaces, right? I think that often gets written off as maybe a simple problem, but when interacting with the body, it's a huge one. I don't know if we're allowed to do audience participation, but I just won a teaching award, so I'm gonna do this anyway, because this is how I like to teach. We have two parts of our body that are made for consistent load bearing, where we can load bear fairly comfortably for large portions of the day. Any guesses what those are? Shoulders and hips are actually, they're pretty good guesses, but if you lay on your hip or you put too much on your hip over time, I'll give you a hint. Most of you are using one of those right now. Your butt is a good one. Yep, so that's one that is well cushioned and well supported. The other that we're on most of the day when we're moving around is our feet, right? So these are the parts of our body that are designed to bear load. If I'm building an exoskeleton that needs to move someone's legs as they walk and needs to hold up their weight, then I get into things like harnesses, right? Straps that go in places that we're not used to, even into backpacks, right? And there may be hikers in here and like, yes, we can do that. We can do that for a short term, but it becomes very difficult long term. So one of the things that we actually look at in my lab is figuring out new and honestly surgically invasive ways of improving the body's load-bearing capabilities, right? And so that's one of the things that we think about is how do we transmit load from an external device to the body. It's especially important in spinal cord injury because they often don't have sensation, so they don't know if a sore is forming, if something is damaging that tissue. And so we're working very hard to try to figure out ways that we can transmit load to the body more effectively.
Great question. Challenges are many. I think the first and global one is really that biology and technology have fundamentally different operating system. We need to learn how to properly access meaningful clinical intervention points and our ability to control them through transduction with various technological means that we have available. So those are the kind of really overarching questions that you got to think about in devising solutions. And I'd also like to step back and remind ourselves that much progress in medicine has been made through technology, which is a great opportunity too. If you think about the humble beginnings and the Hodgkin-Huxley model for the operation of the action potential that models the dynamic behavior of sodium, potassium, and chlorine channels through the membrane, they achieved that remarkable accomplishment through the use of Monroe hand crank calculator. We have far better tools than that today. They received deservedly Nobel Prize for that contribution. Then we have a patch clamp, which allows us to really precisely control voltage on the cell membrane, another Nobel Prize winning work. fMRI, magnetic resonance imaging, 1973 invention, also led to Nobel Prize. So what we see from all of this is anything that improves our ability to access and quantify previously inaccessible information for health, diagnostic, and therapeutic purposes has a major potential breakthrough. I would also like to honor the legacy of UCLA in brain-computer interfaces. How many of you knew that BCI came from UCLA? 1973, if you read Professor Jacques Vidal's paper about brain-computer interfaces, where he introduced this whole idea of BCI lab, it was one of the most beautiful engineering diagrams in which he shows the EEG technology connecting to the brain, decoding that into a computer, and then we used IBM 360 with 4 megabits of memory at that time. And then do all the data analytics and then projecting back on a computer screen to see how actually you can establish kinematic control, accessing somatosensory cortex, and basically doing 2D navigation of a cursor on a computer screen. So when you see now news reports of Neuralink implant playing chess on a computer screen, that's BCI. 1973, in a nutshell. And by the way, that computer was connected to, there was like a bus which says ARPANET. So that diagram displays two inventions of UCLA, the internet and the brain-computer technology, that you see subsequently in New York Times and everywhere published how Monkey from Duke controls robotic arm at MIT Robotic Lab, but two foundational technology underneath are really have a heavy footprint from UCLA Engineering. So just wanted to kind of bring that as a global awareness. So back to the challenge, I think really the ability to increase the number of intervention points so that allows us to get more clinically meaningful points to work from, I think is the largest challenge, which means minimally invasive, but expanding access. So you have to be mindful of the ways in which you can do that. I keep thinking about that constantly, higher channel count, the ability to simultaneously sense and stimulate the brain. And then another challenge there, technologically, I find a lot of really interesting problems that we bring into electrical engineering from these applications. When you think about, let's say, communications industry, you see all these front-end amplifiers and people go into the medical conferences and say this is a low power, so it's biomedical, but you have a chopper-based amplifier which has insufficient impedance for preventing tissue necrosis and DC currents. Anyway, so you have a higher signal when you come closer to the base station. So you can drop the gain and increase the noise because the signal-to-noise ratio is good for reliable detection. But when you have stimulation artifact in the brain, nobody amplifies your neural signal. So you have to have a much higher linearity. And Professor Abidi is really a great collaborator in this space to kind of bring together technology that can deal with these issues of really full duplex technologies that can simultaneously sense and stimulate without blanking stimulation, and the ability to trigger stimulation finally to the natural rhythm of the brain for peaks and troughs of data when encoding and retrieval of memory happens. So all of those are the kinds of features that we are embedding in our technology as we go forward, and plan to engage a large number of clinical stakeholders to give these tools to all the clinical institutions we can have access to gather much more real-world evidence data and see major transition in the clinical space in the next 10 to 20 years to enable new therapies. So those are the challenges we're actively working to resolve.
Thanks, all. That was super interesting. I want to kind of pull out two things that Tyler talked about. One is he mentioned having exoskeletons to help you walk, and that's in some ways restoring a function that we've lost. And then the next thing he said was about, well, I want to swing a golf club as well as Tiger Woods. So that's kind of bringing us to the limit of what I'll call human ability. And so something I think is worth thinking about and discussing is, what about going beyond human ability? So with each of your technologies, I could imagine ways that you could have superhuman capabilities, for lack of a better word. And I think it'd be fun to talk about this in two parts. One is, what do you think is possible? And the second is, should we be doing it, and what are the ethical limits or the lines that we should draw? Because I think that it's not a cut and dry discussion. So I don't know if you want to each take a turn, and then we can debate it.
Yeah, no, I think this is a really important question. And actually, I teach a class on the biotechnology of cell therapies. And one of the assignments in this class is from first principles, I have the students engineer an immune system. If they could, forget about what we know about B cells and T cells and neutrophils and all this. From first principles, how would you engineer an immune system? What features would you include in that immune system? And they come up with some really crazy ideas, like these cells that are decoy cells for viruses and all sorts of things. And actually, in some cases, we go to the literature and we find this is actually something that's happening in the biology. So some cells secrete what we call extracellular vesicles, and they can actually be decoys to capture viruses. Or cells that sense the metabolism of another cell, let's say a cancer cell that has high metabolism, and kills it because it knows it has high metabolism. There's actually, it turns out in the biology, in our human biology, we have cells that recognize, T cells that recognize metabolites that are being produced in other cells, and they can kill cells based on the metabolites they're being produced. But I think the point here is that biology is another language. It is another programming system, and definitely there's capability to engineer it to go beyond what we currently have. Another thing we do is we compare the reptile immune system with the human immune system. Reptiles have what are called natural antibodies. So we adapt over time. As a baby, you get antibodies, and over your years, as you get sick, and as many of you have young kids know that you get sick often, you get your immunity. But reptiles actually have genetically encoded antibodies. Would it make sense to genetically encode in all of our babies antibodies against some of the most dangerous diseases? Now, then it becomes the question of, should we be doing this? When we think about germline engineering, what that means is that we're engineering now not just my DNA or my body, but we're engineering all future generations, right? It's going to pass through the germline. That becomes very ethically difficult to justify, because there's so much that could go wrong, right, as it propagates through humanity, right? And then you can start to imagine some of the kind of science fiction scenarios where you start creating different classes of people that have superior genetics versus non-superior genetics. So I think that there's the things that we have to really grapple with if we start to think about this. There might be cases where the benefits outweigh the negatives. The lights outweigh the shadows. I was just at a meeting where we talk about the lights and shadows of technology, and there's always light and there's always shadow, right? And so we have to identify the cases where the lights outweigh the shadows.
Yeah, I'll say I'm an optimist on this one. So I think the first thing to know is that we're in terms of the things that we're working on in my field, we're not far from being able to augment. In fact, there are companies out there right now. Skip is a good example. Came out of X. They make an exoskeleton in collaboration with Arc'teryx, which is really just like robot pants, and they make it easier to hike. Right, and I think you can rent. I don't remember what they're charging, but you can rent them for a day, or you can buy one for $5,000 and have these magic pants that help you hike and make it easier to hike. And I think there's that maybe that feels safer than something that lets you punch through a wall or run 100 miles an hour. We might start to get a little more nervous. But the first point is that the technology to do this is pretty close. Right, motors are there. Power supplies are getting there, right? Interfaces, we go back to the same thing I said before. The interfaces are still a challenge, but we're working through those. And I would say in the next 10 to 20 years, physical augmentation in this way will be something that we're all looking at what shoes to buy, because we might be able to get the motorized ones that help us walk faster or make us use less energy when we walk. Okay. The question of whether we can, or whether we should, is a more challenging one. The first the first paradigm I want to break a little bit is this idea that there's a difference between restoring someone back to baseline and improving their function beyond baseline. That's a comfortable distinction for us to draw because one we feel ethically comfortable with and the other might introduce some questions. But the reality is it's all increasing performance on a spectrum. And it's normalized to some arbitrary baseline. Like we've said, well, if I'm below baseline and coming back to it, that's okay. If I'm going beyond it, now I've got an ethical dilemma. The reality is that that baseline is arbitrary. And it changes on a daily basis or a weekly basis or a monthly basis. As our bodies change, right, depending on how we're feeling, how we're doing, our ability to perform certain tasks changes dramatically as well. So I view this much more as, if we abstract away from this concept of sort of a binary, we're either rehabilitating or we're augmenting, and all we're doing is we're improving, then the question simply becomes, is the improvement that we're giving worth the cost of that improvement? And that's a question that I think we can ask ourselves in different contexts. The other point I want to make very clearly is that we're already doing this. Right? And I want to give two examples of what I mean by that. The first is in everybody's pocket right now. Right? Your cell phone, your smartphone is a memory prosthesis. It's an information gathering prosthesis. It's a communication prosthesis. And it was introduced, I hesitate to say that it was, 15 years ago now that the iPhone came out and something like that, and we all started. And now suddenly, over that time, I won't even say that costs have come down because they really haven't that much, but everyone has just sort of adapted their budgets because this is such an important part of being a human now in sort of the professional environments in which we exist. Which brings up an interesting point, which is access, right? Anytime we think about augmenting, we think about creating advantage, we also need to think about access and making sure that access is not restricted to only a certain subset of the population. Okay, the cell phone, the smartphone's a great example because access has worked. Right, people have figured out it's been democratized enough that people have figured out how to make this work. The other example I want to bring up is the car. Right, so the car is not quite. It's not attached to our hip as much, but it certainly does augment our ability to move. When I was learning to drive, I got into the car, and my dad was sitting next to me, and he turned to look at me and said, "Tyler, the one thing I want you to know is that you are sitting in a 2-ton killing machine." Right? And the truth is, he's right. Like, cars cause how many deaths a year, right? And yet, we as a society have decided that the benefit we get from the accessibility of that transportation, of moving to one place to another, outweighs the cost of the deaths that happen when people misuse the vehicle or the accidents, right? I see people hand juggling, and I think that's a fair reaction, but the reality is that if we hadn't decided that, then we wouldn't have cars everywhere, right? We would have probably, so in legislating these, in making these mainstream, we have said that, okay, we're okay with that. Not to mention the impact on the environment, right, or other things. We have decided that the benefit of this tool is valuable enough for us to use it. And I think most people use cars appropriately. There are rules in place. We have legislated around them such that there are guidelines as to how to use a car effectively. We can imagine a world where there are guidelines for how to use an exoskeleton appropriately, right? How to use a prosthetic device, an augmenting device of some kind appropriately. So as I've said, I'm optimistic about this. I think these technologies, not only are we relatively close to having them, but I do think that they'll be sort of a slow flow into the market. They'll become more mainstream. They'll be commercially available, and we'll start to all benefit from them. From, I don't know, maybe in 10, 15 years, we have the ability to go run through the woods for 3 hours with one of our children and enjoy something, have an opportunity that we didn't get to have before, right? Because this tool now exists for us to do that. So that's my optimism on it.
My story, I hope, should be very simple and clear. Access is the key word indeed, and when it comes down to active implantable medical devices, I would say that the possibility to even accessing and then offering some sort of augmentation is inversely proportional to the level of invasiveness. So if you think about, this is a very small space. In the medical implants, the whole industry is now pretty much in the chest-based implants, which is about 10,000 units per year. And you'd be surprised that despite overwhelming success with treatment of Parkinson's disease, the adoption rate is only 7%. 7 out of 100 people say, okay, I'll go for it. There is many factors, which is a topic for a whole nother discussion. But on the other hand, we have a hugely underutilized opportunity of intracranial epilepsy monitoring in neurosurgery, which is 150,000 cases per year in the United States. So we are not even anywhere close to fulfilling our, I would say, social responsibility, and I would use another strong word, ethics, to even solve jarring and really astronomical medical problems before we can even begin to talk about any sort of augmentation. So I would just completely leave augmentation aside, although many comorbidities exist, and for example, patients with epilepsy ask, doctors, can you improve my memory and so on? And I work with clinicians who study memory, and it's really interesting from a technology point of view and so on. But we still have a large list of medical issues that we really need to focus on before we can revisit this discussion. I hope we'll be able to do so in the next decade or so when we have better solutions to medical issues.
Can I push back on that? Okay, so I think I hear what you're saying, but the underlying assumption there is that we have an ethical responsibility to treat disease before we improve performance in other ways for other people. And I think that, again, depends on this distinction between rehabilitation and augmentation that I would say is a fairly arbitrary one. If we are increasing opportunity, right, then isn't that universally good? If we're opening doors across the board for people to have experiences that they wouldn't otherwise have, are we to say that one is more valuable to work on than the other?
I still think that it's very the first and foremost, we gotta have a solid therapeutic solution, and it's comprehensive. So I'm thinking in the context of active implantable devices. So I'm not saying that externalized devices which can be used for rehabilitation without involvement of active implants, that's definitely a whole space on its own. But in the context of implantable devices, we still have a long ways to go in that space before we can even get to the augmentation part. Yeah.
I kind of have a question about that, because I feel like, one is implanted device, one's exoskeleton. And I feel like there's a maybe artificial, but a psychological difference between things we're putting in our body and outside our body. So for example, if you told me I could have glasses that make my vision, I can zoom in like a microscope sitting there, I'd be like, that's awesome. If you said we could do it and replace your eyeball, I would say, I don't know. And so I feel like we have a squeamishness, and I don't know if that's artificial or what, but I mean, you guys are kind of talking about technologies that do similar things. Dino, you look like you have a comment.
I think the boundary is reversibility. So if it's reversible, so taking something off and on, but something that's replacing your eye is probably going to be a difficult thing to reverse, right? Also, gene editing, right? So if I edit my genome, editing it back is not an easy thing to reverse, right? So I think reversibility is a key aspect of like where that boundary is.
Yeah, I would agree. I think that's actually a critical idea. I actually work mostly in surgically invasive stuff. My lab's kind of, the vision that we have in the lab is that we want to engineer the body in parallel with machines so that the two can work better with each other. And one of the key tenets of the work that we do is we always try to identify pathologies, right, problems in medicine to which we can apply the technologies that we're developing, where if something fails, we can reverse what we have done without leaving the patient in any worse problem where they would have been. So one example is we're working on orthopedic implants that function in a completely different way from a standard knee replacement. Where standard knee replacements roll, rub, and slide, we're making ones that move by bending and deforming, so like a spring that you put in to replace your joint. And the hope is that this can last a lot longer. We're starting in the ankle, right? And one of the reasons we're starting in the ankle is that there's a subset of pathologies in the ankle where the only options that exist right now are extensive fusions and amputation. And so there are there's this I wouldn't say a lot, but there's around 5,000 patients a year across the US who choose to amputate their foot because one little bone in the middle of the ankle is damaged irreparably. And so that's a perfect starting condition, right? Because we can if they want to amputate anyway, we can go try this implant and say, best case, we save the foot. We give you the function back. The pain is gone. We save the foot. Worst case, we cut the whole thing off. And yes, amputation is irreversible, but they were going to do that anyways, right? So we've left them where they otherwise would have been. So I agree completely that I think a fundamental concept here is that the risk that we take and the risk that we're comfortable with having a procedure done. And I think we are still in a place where the risk of surgery is high, and higher than I think most of us would be comfortable with, unless the gain in function is so dramatic that it is life-altering.
I would just say that that's an interesting thought here. It's important to factor in with miniaturization of technology, and in implants there are really two trivial things that are key limiters. It's not electronics. It's the size of batteries and connectors. So mechanical issues, body contacting materials, better battery technology, and I think about the roadmap in which we can move away from chest-based devices that are used to treat problems in the cranium to moving them up in the cranial space where you need rechargeable technology because incisions in the head do not heal nearly as fast as quick and easy access to pectoral area. And then even going to minimally invasive or less invasive like endoscopic surgeries, the kind of things that we do for treating brain aneurysms through the hip vein or ENT type of surgeries, where you can see these specialized focus areas be treated with much less risky surgery. A couple hours, perhaps it's almost like going for a plastic surgery, you just had a brain surgery. So going in that direction, I think, is a path to increase adoption and get more meaningful treatments.
Thanks. I think we're almost wrapping up, but I don't want to put you on the spot, but I wanted to give you a chance if you had a 1-minute thing on to say about, is there something that you're the most excited about when you look about what my future might hold in 20 years with respect to this healthcare? What's the thing that you think, all right, this is going to make my life a lot better?
Yeah, I think that we're now at a place where with some of the new delivery approaches for mRNA and other things, that we can start to engineer, not in a non-reversible way, some of the cells within our body in a very precise way. And that, along with our ability to understand the communications, how these cells are whispering to each other, that will allow us to treat a number of different conditions: autoimmunity, Alzheimer's, cancer, a number of different conditions that can leverage the fact that we can introduce new functions into our cells in a very precise way, with very simple treatment approaches. So, something that's infused within your bloodstream. So I think very excited about where these mRNA-based in vivo programming technologies are going.
It's a really exciting time in bionics because there's a lot of sort of parallel fields that are coming together for the first time into systems level improvements. So things like motor, I mentioned a lot of them before, but motor development and battery technology and control systems and bringing in AI now. And so the thing I'm most excited about is to see these systems come together and truly start to restore movement ability in ways that has not been possible before.
Yeah, I also see a great opportunity for an intercept between modern brain-computer interface technology and data analytics that will provide miniaturized, minimally invasive, personalized therapeutic solutions for people that are closed loop and as compared to what we have today, mostly open loop and a lot of issues I happen to know firsthand from talking to patients with implants. So I see a great opportunity in that space to bring a personalized solution. It's kind of a digital pill augmenting pharmaceuticals. This is your recipe. We can monitor and track in a large database and give people personalized solutions.
Thanks, guys. So I hope you will join me in giving a warm round of applause, and thank you for our panelists.
Wow, what an incredible conversation that was. I don't know about you guys, but I was just like feverishly taking notes and just completely geeking out there. And just for the Cliff Notes version, there were 5 things that really just kind of stood out to me. There were just so many gems there. The first was that risk relationship between what's implantable and what's reusable. The second was technology emits lights as well as shadows. Let's maximize the lights. The fact that UCLA and this field is going beyond the scope of human ability. The fact that UCLA was also the inventor of brain-computer interfaces. And the fact that technology and biology have different operating systems. And so we have to think of integration as a grand challenge. Wow, that was an incredible talk. So thank you all so much once again. And now we're going to seamlessly transition to more awards. And very excited about these next 2 awards. The first is the Alumni Service Award. And what a meaningful award this is for our engineering community, our alums coming back, giving their time, giving their talent, giving their treasure to a place that has inspired them so much. And it's my great honor to present the Alumni Service Award to Yue Du, who is currently the Director of Digital and Data Systems at Caltrol, which is a controls and process automation company here in Southern California. But Yue having an exorbitant impact on the Engineering Alumni Association, having served on the Engineering Alumni Association since 2016, and for the last 8 years serving as chair of the Student Projects Committee, really building those external relationships with companies in the spirit and pursuit of the student experience. So I invite Yue to present this award and invite the Dean as well. Thank you so much, Yue.
Is this on? All right, great. So before I get started, I would like to say, if anyone has, done any of these awards or presentations for a large company or organization, normally they ask you to submit some sort of like script or outline or something like that, right? So I asked Brian, our amazing rep, how do I do this, right? Are there guidelines? Are you have anything given? He's like, no. We trust our speakers. You can do whatever you want. So if I say anything off color, it's Brian's fault. Blame him. All right. So first of all, most importantly, thank you, EAA. Thank you, everyone here, for nominating me for this award. It's an honor being up here with leaders in industry, leaders in research, imposter syndrome all over the place right now. But, I just want to say most importantly, right, everyone's heard it takes a village to raise a child. That doesn't end at 18. It keeps going once they're in college, and I'm a prime example. I had tons of help from parents, from other students, from staff, from alumni, everyone across the board when I was here as a student. So really, I just want to be able to give back and, honor those who put their effort and time into me by passing that along to the next generation of students. And I implore all of you guys, do the same. We have some amazing student projects that are going to be setting up shop during the reception later tonight. Go talk to them, grill them on technical aspects of their projects. They can take it. So anyways, great, time is up. Before I go, I want to say, Henry, congratulations on $1 trillion company. I will drop off a resume on my way out.
Get in line, Yue, for the resume drop-off. The next award is the Rising Professional Achievement Award, and this is an award that's particularly special to me because I had the opportunity to win this award a few years ago. So really honored to present this to Capella Kirst, who has been an absolute visionary since graduating from UCLA Graduate School in 2014, co-founder and CEO of a bio-inspired company that delivers bio-inspired adhesive solutions, Gecko Materials. The company was a Bruin Business 100 company. It was the runner-up in TechCrunch Disrupt in the Battlefield pitch competition, which is the most notable startup pitch competition in the world. And while Capella was here, she was the founder of one of the most popular today student-led hackathon organizations, LA Hacks. So just the full gamut of research, industry, service experience. And so we're so honored to have Capella here to accept this award with the team.
Thank you. Wow, what an honor to be up here today receiving this award from my alma mater, and wow, what a privilege to follow in your footsteps. I am completely honored and humbled to be here. God has blessed me with tremendous vision, path, and opportunities, such as going to UCLA. I'd also like to thank my employees at Gecko Materials. They are exceptional. I am so blessed to have each and every one of them. And last but not least, thanking my mom for her support, sacrifice, love, being my #1 fan, for which all of my success and achievements I've ever received has been at her cost and her just thank you, Mom. I'd love to just share just a little bit about Gecko Materials and the vision behind it. It is a public benefit corp, which I got from UCLA's, just giving back community, which I love so greatly. So Gecko Materials is a bio-inspired dry adhesive company. 1-inch tile supports 15 pounds vertically. 6 1-inch tiles can pull a car, and you can reuse it over 120,000 times. We call ourselves the next industrial Velcro. Velcro, for reference, can only be used 2,000 times, so we're stronger just a bit, and hopefully are helping our customers save energy, time, and money. We're currently on the International Space Station. We sell to companies like Honda, Ford, Toyota, BMW, Samsung, TSMC, other semiconductor companies here on Earth, and again, continuing to help them save energy, time, and money. So it's nice to contribute back to the semiconductor industry that UCLA has so been the forefront and runner for. So hopefully, again, Gecko Materials shows by example, by also manufacturing locally, as well as having all of its raw materials sourced locally as well. But being a leader with compassion and vision also has to come with, again, looking at the public benefit corp, leading by example. So because UCLA has so inspired me to do that, we set up as a PBC from day one with a little bit of pushback, but now I challenge other companies to be for-profit, but also have a mission statement in which we're helping our surrounding communities. All of our employees are paid 1 day a month off to give back to the community. And again, that aligns with our mission statement, which has been a great opportunity. So I truly love and value, again, UCLA's moral and ethics, the Order of the Engineer being one of the few UCLA schools in which we have the Order of the Engineer to lead morally and ethically, has just been an underlying kind of during my time here at UCLA, and then continuing that to my business. So I'd, again, love to thank the awards committee, my team, my family, my mom and God, and all of you, my fellow Bruins, who continue to inspire me daily. I'm just so thankful for you. So I challenge all of us to continue having a brighter, greener future together. And thank you, and go Bruins.
Go Bruins. Go Bruins indeed. Thank you so much to both of you. What an event it has been so far, and we're only at halftime. So my next announcement is break time. And I think, Christine, it's 20 minutes after the hour. We're coming back, so 20 minutes after the hour. Stretch out, check your phones, socialize. Bruins won by 25, by the way, 2 in a row against Michigan State. We'll be back in a few, folks. All right, everybody, welcome back. Hope the break was good. Hope the opportunity to connect with others was really meaningful. That's what some of these events are really all about, is the opportunity to reconnect with others that you may not have seen after a couple of years, an opportunity to re-engage with the school. That's really why we're all here together in an overarching fashion. So really excited about our next panel. And while I invite our panelists, our distinguished panelists and our moderators to the stage. We'll provide a little bit of context. So Professor Kim, Professor Ma, Professor Peng, and Professor Soato, if you could please join me on stage. Panel number 2 is Perspectives on AI and Intersections. We can't have an event today without some conversation about AI. So really excited about the conversation here. I'll just frame it for a second. The best way I've thought about AI, and I'm really excited to get the perspective of the experts here, is that the marginal value of data has gone to zero with access to the internet and other technologies. And then in the 2010s, the marginal value of pattern recognition in the form of business intelligence and rudimentary pattern matching went to zero. Now we're living in a world of the judgment layer. And how can AI unlock greater and greater judgment for individuals that require such judgment in their jobs and open up the capacity to make humans human, whether it's from a critical thinking standpoint, a complex decision-making standpoint, or really building on intuition when dealing with nuance. So with that, I will hand it over to Professor Soato and our panelists. Thank you so much.
Thank you, everybody. It was a fun and engaging panel just earlier, and so hopefully we'll follow up. My name is Stefano Soato. I've been a member of the Computer Science Department faculty for a quarter century. So I joined when this was merely a School of Engineering and Applied Science. That was before it became the Henry Samueli School of Engineering and Applied Science. So, so from that perspective, I represent the old guard, the one that has to be dismantled to leave room for the young and smart who are here for us today. They're a lot younger, no less accomplished, of course. So Nanyun Peng is a colleague of mine in Computer Science Department. Jachi Ma and Young Seo Kim from the Civil Engineering Department. The title of the panel had to do with intersections, with presumably has to do with the fact that AI is not just a domain of computer science departments these days, but has kind of affected beyond all departments in academia and, of course, society. How many of you have not played with ChatGPT? Ever? Okay, 2, 3, interesting, 4. Very good, very good. Okay, so we have the experts here, both in terms of developing these models and using them in applications that have very broad and deep societal impact. So I will start with a softball for our panelists, which is to introduce themselves and tell us how they got to where they are, how they use AI. And but I would like actually to engage the audience because there are hotly debated topics, as you imagine. I wear a dual hat. I'm on leave currently as a VP of Science at AWS. And there's a very interesting interplay between academia and industry. And certainly many of the developments that they are leading do impact already the life of many, you included. So I encourage you to please raise your hand and I'll bring in the questions. But I might have pressed inadvertently. Hopefully from the back they will recover the screen. So do you want to start, Nanyung? So please.
Sure. I'm Nanyun Valley Pan. I'm an associate professor from the Computer Science Department. I work on natural language processing, which is a domain that work on the core AI capability to teach AI to understand, thinking, communicate, and collaborate with human language, which is natural language. And how do I get into this field? It's actually a long story. It was 20 years ago, I entered my college, and there was this new, I think we're the third iteration of that new interdisciplinary field called computational linguistics, which is just teach computer to learn human language. And back then, it's just so uncertain. So I explored several things under my undergrad. I actually hold dual degree in computational linguistics and econ, and basically look a lot through humanity. But then I also basically studied this engineering, like computer science, and then I finally stuck in this stuck in engineering, and it's really fascinating, and we're making progress on equip AI with the capability to really naturally communicate and collaborate with human. Yeah, that's my story.
Good afternoon. My name is Jiaqi Ma. I am a professor at Civil Environmental Engineering. I also kind of affiliated with the John Garrick Risk Institute. I do a lot of risk analysis as well as part of my research. I graduated from a department called Systems and Environmental Engineering, which is kind of difficult to know what exactly it is. But what we did is learn all the data courses, all the optimization courses. And then when I graduated, I got into a company, and they threw like 5 vehicles to me, 5 automated vehicles. Hey, get it moving, basically. I was like totally clueless, because when I was a PhD, what I did all about optimization, data, training linear regression models. But then all of a sudden, I have to really get into this robotics and autonomous vehicle world to make it working. And then that's where I really had to, really study AI on the side, and my day job is get a vehicle moving. My nighttime is studying all the computer vision algorithms myself. But gradually, luckily, I was able to make those 5 vehicles working. We did some amazing experiments actually on for the U.S. Department of Transportation, because that lab was funded by the U.S. DOT, and we were able to demonstrate a lot of new kind of infrastructure vehicle collaboration concept as part of my work. Now I run a center called the Mobility Center of Excellence at UCLA. This was also started 3 years ago, funded by U.S. Department of Transportation to perform, to basically bring these autonomous technologies at scale deployment throughout the nation. And gradually, over the past 3 years, we have engaged with a lot of the local agencies, state agencies, also a lot of companies as well, really trying to help them to deploy these new technologies, including AI, including automation, and many other computer vision into the daily operations of different public utilities, transportation systems, and so on. So that's kind of my story, dealing with AI every day. I was joking to my students, AI is in every corner of our lab, and you guys have to code to make them work. That's my story.
Hi everyone, my name is Young-Suk Kim. I'm an assistant professor in Civil and Environmental Engineering Department. I recently joined UCLA in this July, and before I joined as a junior faculty, I received PhD at Cornell University. So it's quite exciting for me because it's first time panelist, and also I wouldn't even get invitation until this May, but I suddenly serving as a panel, so it's my great honor. So my research domain is transportation and logistics and smart mobility system. So I use AI in my research, and before we talk about AI, I would like to define my perspective of AI. So I know that typical definition is usually refers to machine learning and deep learning, but my definition is a bit broader. So I would like to define it as automated decision-making system that can solve problem as good as human experts, or even at a scale that human expert couldn't even solve within their lifetime. So that's my definition of AI, and I use optimization, like system level optimization at a core foundation, and use deep and machine learning to make optimization problem faster or basically improve its performance.
Great, thank you. So again, if you have questions or if you have comments from the audience, feel free to raise your hand at any time. But obviously, everybody has an opinion of the fact that AI empowers a lot, but it also presents some risks. So I wanted to get your perspective on what you think are the most pressing problems that we should and can solve, being in academia, but also being in LA, connected to the broader environment, LA, and industry within LA and the broader country. So what are your perspective on what we should be doing that we're not doing and can do within academia? So you want to start?
I can start. I think one of the most pressing issue of AI, actually there are two. I think both are very pressing. One is the safety issue, because if you guys watch the news, you probably know that in August, there is a California 16-year-old kid committed suicide successfully by communicate with ChatGPT, despite there are quite a lot of like guardrails in place for this, but in general, these models are still vulnerable in terms of when you're, for example, that kid, he probably know enough, like more than enough AI to learn to use some of what we call jailbreak, which is they fool AI to think this problem is not harmful, and what he did is like, I'm trying to develop a character, and this is like everything is fictitious, and he was able to trick the AI to verify his suicidal approach, like whether this way of tie the knot can hang himself, and he was succeed with that. I think this is super concerning, and I think it's just it's our responsibility as builders to make sure we also have all the necessary guardrails in place to identify these harms, escalate, and being companion, and in the meanwhile being helpful. Another thing that I think is very important is the ownership of AI content, because I work on AI creativity. The idea is one day AI can start to produce movies and we watch, music we listen to, books we're reading, etc. And there is a lot of pushback in Hollywood, and I think there is a lot of like legal debate on whether like what is fair use of AI, of training on all those human proprietary data or people's writing and all that. And I think this is also a pressing problem that we need to basically find a definition of fair use, and then define what is like it's okay for the AI to use and what is not okay, because at the end of the day, we want AI to be a very useful tool. It's helpful for every aspect of our life, rather than bring any sense of threat to our life.
Okay, thank you. So, by the way, Nanyu, when we hired her at UCLA, her domain of expertise was puns, meaning having machines generate jokes. So, and maybe we miss that a little bit of that in our lives right now. But this is Joshi.
Sure. So my work has been related to AI, has been applying AI, making sure AI works properly in real world, especially the safety critical systems. Because, for example, a couple of areas I work with, transportation, vehicles, these are the areas where you just can't make mistakes, right? When you play with the ChatGPT, ChatGPT hallucinating a little bit, you can reconfirm, are you sure, right? GPT will always say, oh, I'm sorry, I made a mistake. Always say that, try that. He will always say sorry to you. Yeah, but there's no chance for in a safety critical system. There's no chance to say sorry. So because I work with public agencies a lot, including state and local, and also federal government. About like 3 years ago, when there are the whole AI hype started, and almost AI is deployed in every systems in your life. Right, starting from transportation, public, any type of public works, right, utilities and water systems and so on. So almost any system, and then all the in our field we talk about transportation and mobility. We would like to answer this question: are these systems deployed in the real world, on the roadways, at the intersections, roadway intersections, really gonna help you, right? We don't want them to generate a lot of false alarms. We don't want them to miss any pedestrians that might be hit by a vehicle, but guaranteeing that is non-trivial. So about 3 years ago, our lab and also actually state and local agencies started working on this concept, either testing, evaluation, or verification and validation of AI systems. I know recently, even in California, there's a new bill being proposed, and it's coming out soon, that it's called, basically, you have to have an auditing process to audit all the automated decision systems in any public work systems, including transportation and others. So this is very much aligned with the work we are doing. I think this is exactly the thing that we have to do now, especially in the safety critical systems that that will be potentially endanger people's lives. So the other area I think is going to be of interest, especially for academia to work on, is to create some platforms, pre-competitive platforms that will enable innovation. I know, especially the model of a computer science of open data sets, open platforms, that has been a very great model. So in our field, we don't have that much in the past. However, in the past couple of years, because of the new systems coming in, we are building open platform, open data sets as well, just to test different technologies. Just one example is that one of my colleagues in California, Department of Transportation, he came to me that, hey, Joshi, all these LiDAR companies are talking to me, say their LiDAR is the best in the world. They want to deploy at our intersections. How can I even know they're the best in the world? Then I told them, hey, we have a smart intersection here at UCLA, and we are providing you all the data sets. Get their LiDAR to me, right? I will test it for you, right? We are common data benchmarking, common platforms. We'll test all the platforms. So actually, we have a project now developing that platform. So I think this common platforms to enable testing, evaluation, kind of back to my first point again, is very critical as well.
Please.
Yeah, I would like to add up the point that Joshi's points about all the AI hype and the belief of general people that it can be applied to any field, which is not actually true. We definitely need to develop technology and better model. So I'd like to talk about modeling aspect. So unlike other fields that data-driven method can work, transportation problem has unique challenges. So first, we are involving physical network and also operation constraints. So for example, vehicle cannot teleport, so they need to move along the roads, and they need to satisfy the capacity limits, and also they need to follow all the operational constraints. And the second thing is that transportation problem involve a lot of complicated human behavior. So human make decision on the road network. They decide destination roads, modes, based on their perception, incentives, and their convenience. And it's really complicated to model. And there's been a huge literature about it in behavior science, how to model these, how to build a statistical modeling, which is interpretable. So going back to the AI area, if we just apply data-driven AI to transportation field, it's highly likely that we got infeasible solution. What I mean by that is the solution they guide might violate some physics law, or it doesn't follow the principle of the behavior science. That's why we need to build model that is principle-based. So what I envision is the model that can integrate all those kind of multiple discipline. So it's as flexible as deep learning and machine learning, and it's as interpretable as statistical modeling, and it's as rigorous as optimization. So this is how I envision the future of AI, especially in transportation domain.
Thank you. And this is a counter-current point of view. And so I think different people stand on different sides. So I would encourage, if anybody in the audience has a question there, please.
Well, I sort of have a question, comment. I find it kind of curious that we tend to hold AI to a higher standard of safety versus human beings than we do other tools. How many people have hung themselves with a rope? How many people have killed themselves with razor blade? If somebody hangs themselves with rope, we don't say, what's wrong with the rope? We shouldn't sell rope. We say, misuse of a tool.
So for those of you who couldn't hear it, let me summarize the comment, which is that we seem to hold technology. I would state that for technology more broadly than just AI, to a higher standard than human behavior. In fact, I have to say that over the past 5 years, the most stunning thing that I've learned in AI is how bad people are. And it was mentioned earlier that every year we kill about 1.2 to 1.5 million people every year out of traffic accidents, because we're talking about mobility here. And this is people, but societally we are accustomed to that. It's an accepted cost of the freedom of individual transportation. But what is the acceptable number for technology to do the same? But if you look around, the acceptable number is zero, and essentially zero. And so I think that it's fair, but I'm interested in the opinion of those who are directly involved. I would just mention that I actually got into first control systems, then computer vision and AI, because of work of people, particularly Ernst Dickmans. I don't know how many of you know who Ernst Dickmans is still alive. So, but you know who Elon Musk is, right? So Ernst Dickmans in 1984 had a full-size Mercedes van operating on public freeways at speed up to 90 kilometers per hour. In 1994, demonstrated an S-Class Mercedes-Benz going autonomously from Stuttgart to Charles de Gaulle in Venice. And so he had the whole thing, and he had written books, and he is not acknowledged by most people, even those working in the field. But he has thought through many of these questions. And if you read these papers, which are technical papers, it cites Kant, Fichte, Schelling, Hegel, all the philosophers who have addressed some of these not only ethical but also metaphysical issues. But coming back to the question of why should we hold technology to a higher standard than society, or if we do, what is an acceptable level of risk that we accept from technology that we do accept already for humans? Yeah. Matt.
Can you hear me?
Yes, I can.
So, when you're talking about safety and we're talking about what guardrails we should put, we have to first understand that AI is not just one thing. There are certain aspects. Thank you. So fundamentally, there are two things we use AI for. One, it computes faster than you and me. It can handle a lot more data than you and me. It is much more accurate than you and me in terms of defined elements. The second thing, where Professor Ma, you were talking about, transportation. I'm involved in that for smart cities and stuff, for the Transportation Research Board. That is quite different. That is not just based on the speed of computation and training and so on. It is also very heavily based on machine-centered learning and pattern recognition, because you're not going to come across the same intersection every time. And not all signal lights will be the same. As it has been proved, making a left turn at a signal light causes 63% more fatalities than anything else. So when we talk about guardrails, I think we have to qualify that you cannot just take a technology, compare it to a human, and say, well, this is the thing we put on it. One, the training data. Where does the training data come from? You, me, and others. Our inherent biases is what it is trained on. It's not creating all this by itself. And then we say it hallucinates. Why does it hallucinate? Once again, the data that has been provided by you and me, that is our hallucination that it's actually following. It may not be yours and yours, but it's somebody else's. So putting guardrails on something like that cannot be done after the fact. You have to first make sure the kind of data you're training the system on, the human-centered machine learning that you're using, and the number of variables and pattern recognition that you're using. So there are three different aspects to AI, and you cannot have one guardrail for all three of them.
And I believe the aspects are represented by our faculty here. So would you like to comment on that?
Yep, I can quickly comment on this. I think it's totally agree. And even in some of the frameworks we are developing now, we're looking at the entire life cycle of this system development, right? Not just during operations, during inference, but we need that's why we call it verification validation, right? There's a components and model pieces we need to verify. There are the whole system when there are operations, we need to monitor, keep looking at the performance and so on. And so that's the entire life cycle of any engineered systems, right? The V diagram we are also familiar with. We're looking at really the entire life cycle. And the other question about that is that in my center, our daily work, we work with autonomous driving companies a lot, Waymo, many others. They are doing their best to convince, right, our vehicles is at least as safe as the human drivers, right? This is kind of what their approach now. It's very hard, right? As you said, every intersection is different. So there's a lot of out of distribution data scenarios that Waymo vehicles these days cannot handle. But the good thing is that we have more intelligence these days with these AI models. They can potentially, there's a generalization capability, they can handle better. But overall, still the same thing, right? They cannot handle some scenarios as good as humans. They handle much better in some other scenarios. And overall, there's a whole big area of public acceptance of these technologies has been up and downs, up and downs. Every time, Tesla has some problem, they go down. Then every time Waymo deploy more, then it goes up. So it's a very intriguing whole discipline that, these companies are looking at.
I can comment on the safety comment because I think I sort of brought up this issue. I don't think we're particularly take a higher standard on the technology because I think my view on this is AI becomes really strong now and it can understand your meaning and can understand your intention and it becomes an enabling tool. When anything becomes an enabling tool, I actually agree with you that it's not the tool, it's human, but the issue is whether we should have regulation on what will you use this tool be, and should we ignore the potential if this become an enabling tool for a bad person to achieve bad goals? Should we just sit on it and say, oh, it's not, it's just a tool, and we don't do anything. And I think there are many other examples. For example, people are working on genetic editing, and it's not to say we shouldn't work on the technology, but the issue is you can use gene editing for many bad purposes. We still want the technology, we want it for good. That's why I think have that awareness, and also as a builder there have this, and I also agree with the comment there, it should be in the whole life cycle of AI. It's not like a post hoc thing that we should do, but like just realize there is this issue, and especially when they are strong enough, actually, only when they are strong enough, we need to worry about that. And it's a time for us in a way, as builders, need to be responsible for the user.
And I mean, Asad Mani brought it up, and I think that you have what we call generative AI these days, which I think what Nanyun is talking about, and then we have emphasis on models and an emphasis on sensors. And I think these are very complex systems that we're only beginning to understand. So it's even difficult to legislate or to even predict what the behaviors will be. But it's important that there is an engagement between all the aspects. So I want to give an opportunity to Young-So to comment on that.
Yeah, I think that's a really good point. And I would like to emphasize that academia is starting to understand this complex system, and they try to divide this complicated problem into pieces, and they are working on the area. So one example that I want to give is I bumped into a paper published in Nature, and they talked about how we can train autonomous vehicle, and the way that they generate data is they are augmenting the data by using the driving simulation. So it's like it's a combination of AI and like virtual reality, like augmented reality. That if we use the driving simulation, then like some safety critical situation pops up, so that we can like train how the human driver react to the safety critical events. And that's how they like give more data to the AI so that they can overcome the challenges of like data sparsity of safety critical events. So I believe like as we break down the complex system into pieces, and as you divide challenges into 3 pieces, if we go like try to push forward our technology, as researcher in academia, then we might be able to reach the point that we can trust this AI better than human.
Okay, so we're almost at time. I want to give one last opportunity to anybody who has comments or questions from the audience before I turn for the last question to the, oh wow, okay. Maybe we will not get there. Okay, maybe Jeff and then, yeah.
So I had a question for you as educators. Oh, thank you. No, I can, thank you. So I have a question for you. Okay. No. Sorry, I'll be back in.
We can hear you.
Oh, now you can hear me. All right. I was going to say I'll be back. So I had a question for you as educators. There's a lot of talk now about how teachers are concerned about their students using AI to avoid learning. And at the same time, all those students, once they go into the workforce, are going to be asked to use AI every day. The four of you are perfect examples. I work in the software space. We see a little bit about similar situation where when we interview potential candidates, we used to give them programming problems. Now they can solve those problems with AI. So we don't want them to do it that way, and we still want to judge them. And the minute they come to work for us, we want them to use AI as a key tool in their programming every day. So how do you find that balance and think of it as educators? Thanks.
Can I, before we all take the question, can we hear all questions and then you can choose which one to address? So we had one there and then one there. Yes.
I've already been rejected?
No.
Oh.
You're on hold. Your business is very important to us. Please remain on the line.
So my question gets to the the human-machine interface aspects of this. You know, as humans, we do use natural language to communicate, but if I'm standing here right now and I'm talking with you, there's a whole other bunch of cues you're getting, the tone of my voice, my gesticulation, and so on. It's a very sterile kind of typing at a keyboard, so there's a lot of things, the example I think that Professor Peng gave of that unfortunate circumstance, the AI had no comprehension or conceptualization of what someone's intent was, whereas if that had been a trained psychotherapist, or maybe even the person's parent, they would have gone, wait a minute, this is going down a very dark hole. So my point really is, where do you see the expansion in the machine-human interface so that not only do you get questions, but you really the machine would get a deeper understanding of intent?
So maybe in the interest of time, because Christine is signaling at me, we take 1 minute each if you want to address either questions. Anybody wants to start?
I cannot answer to the question to the concern about how to teach students, how to guide them on LLM, but I do want to add more complaint on it because I'm in a generation while I'm doing PhD, for the first 2 or 3 years I couldn't. There is no ChatGPT out there, but afterward, it started gaining its popularity, and I started to use it, and it was incredibly helpful to improve my writing skill. But at that point, I knew how to use it because I didn't have an access to it, and since English isn't my first language, I couldn't write. I knew that I couldn't write sophisticated sentences. That's how I try to. At least write meaningful sentences, and that's how I build my ability to tell the difference between what is the garbage sentence, what is the meaningful sentence. And I think at some point students need to take time to think and try to do their best before using AI, and then they need to start. Adapting it. That's one of my opinion, and I'm consuming all the time.
Yeah, we're getting a red line. Any 15-second comment?
Quick comment on the education side. Again, I think AI is a tool. Actually, I do realize in my class, I give homework almost every year similar. I always change so that they cannot directly copy, but it's a similar concept, change it out. And over the year, the homework score always steadily get high. And last time when I offer, almost always everyone get 100%, right? But then when it comes to the exam, they stay similar. They still do similar on the exam, which is good, which means they didn't Like it's not, at least they didn't regress in their ability or what they learned. So I think at some point, AI is a tool. It's everywhere. It's really helpful, and we actually should use that during workforce. What is the challenge is let the young people understand they need to put the hard work in to understand what they learned and also understand how to use AI tools, and that will be of long-term use for them, and they just need to understand. And it's tempting. It's like they need to combat with the inner self of themselves, of their inertia or whatever, laziness, and I think it's our responsibility to bring that up. Yeah.
All right. With that, I would like to thank our panelists, and thank you for your time during the
All right, great discussion there on AI, super interactive. I continue to take my notes, and I sort of had 4 takeaways. The first was scope, that we need to have conversations around, in a proactive fashion, around ethics, regulation, verification, validation. The second is usability. How usable can these systems be in real-world settings when you're taking noise into account? That data science problems are different from behavior science problems. And how do we bridge that gap with things like principle-based models? The third is you have to have the open data sets and the platforms to be open source to move along the innovation so people have access to be able to move things forward. And then finally, public acceptance. The most striking thing about AI is how good or bad the underlying humans that are feeding the data are. So really, really fantastic conversation, and thank you all so much again. We are now going to interleave with the 2 most senior awards as part of the Engineering Awards program. The first is the Professional Achievement Award. And I'd love to recognize Dr. Dariush Divsalar, who is a triple Bruin, master's in 75, the degree of engineering in 77, and a PhD in 1978, senior research scientist and fellow at the NASA Jet Propulsion Lab, an individual with 30 patents, over 300 technical papers, and has been recognized by institutions like the Ellis Island Medal of Honor, has received the IEEE Alexander Graham Bell Medal, and was inducted into the National Academy of Engineering. So I invite Dean Park, as well as Professor Asad Abadi, to recognize Dr. Divsalar.
Thank you very much. I am deeply honored and humbled to receive this award. Thanks to Dean Park, Professor Abidi for nominating me, and the award committee. Okay. Being recognized by Samueli School in presence of so many leaders here and faculty members is truly special for me. My gratitude, sincere gratitude, goes to my family for their unwavering support and also encouragement, especially my wife, Giti, and my daughters, Dina and Sharzad. I also want to thank my mentors when I was UCLA student here, and later late Professor Jim Mora, Professor Leonard Kleinrock, and Professor Ishak Rubin, Professor Yao, and finally I should say Dr. Viterbi, who have inspired and guided me throughout my academic journey and beyond. I also like to thank Dr. Samueli, that really over many years supported my research. And also I like to thank Dr. or Professor, I should say, Asad Madni for his support and encouragements. I am incredibly grateful to Associate Dean Professor Wessel and Laura Dolecek, Professor Laura Dolecek, and their students, that their essentially collaboration made this achievement possible for me. And finally, my gratitude goes to the Jet Propulsion Laboratory and my colleagues there for encouraging me and inspiring me to come with a new technology for the nation and for the NASA space exploration. Thank you all.
Thank you so much. Thank you. Thank you so much, Dr. Dufsalar. And now, our senior-most flagship award, the Alumnus of the Year Award, presented to Dr. Fang Liu, again, triple Bruin, master's in 88, engineering degree in 89, PhD in 92. There's a theme here. You need to be a 3-time graduate at least. So it's all about the engagement back with the school. Dr. Liu, longtime technical director of Broadcom, one of Broadcom's first 2 full-time employees. His advisor was none other than Henry Samueli, and truly one of the fathers of building the infrastructure that has enabled content-based subscription and all the business models that we see today. The technical infrastructure was helped built by Dr. Liu. We are so proud to have Dr. Liu represent this great university as the 2025 Alumnus of the Year, and I invite Dean Park and Henry Samueli to present Dr. Liu with the award.
Good afternoon. First of all, I'd like to thank Dean for giving me the opportunity to attend this wonderful event. This is a very high honor, and I should receive with a humble heart. I am always proud to be a UCLA alumnus, and I'm also proud to be a member of Broadcom, which was founded by Dr. Henry Samueli 34 years ago. I'd like to thank all the UCLA professors that equipped me with knowledge and skills to work in the semiconductor industry. I am also grateful that UCLA gave me the opportunity to join Broadcom through Dr. Samueli, who was a professor and my research advisor at UCLA at that time. Thank God that guides me to choose Broadcom in its startup era instead of going to other large high-tech companies. And today, Broadcom's market value has exceeded that of Tesla. It has always been my pleasure to support engineering school in the past 2 decades. And nowadays, some colleges might be facing financial uncertainties. Therefore, I encourage all the alumni, friends, and families to support UCLA generously. And UCLA has been a great school for over a century. So ladies and gentlemen, let's make UCLA great forever.
All right.
Thank you.
Thank you so much, Dr. Liu. And now we're transitioning to what we are affectionately calling our Bruin Talks. So this is going to be 3 rapid-fire, 8-minute TED Talk style discussions here on some key topics that are cross-disciplinary and multifunctional. So without further ado, I want to introduce Gaurav Sant, the director of the Institute for Carbon Management here at Samueli, as he will be providing a talk on translating discoveries into technological and climate change mitigation solutions.
Hi everyone, thanks for being here on a Saturday afternoon. You should hopefully now all be able to hear me. Like Jamal just said, this is Gaurav. I'm going to tell you a little bit about work that we've been doing with the Institute for Carbon Management, which is now, unfortunately, or fortunately, over a half-decade old. To tell you a little bit about the Institute, before I go ahead, I should acknowledge all of my colleagues that are a part of it. All good things happen in company, always not in good company, but in great company. I want to particularly acknowledge Fabian and David, who've sort of been really, really instrumental to the work that we've been doing over the last couple of years, and of course, a bunch of my other colleagues, both in engineering and the School of Sciences. To tell you a little bit about the Institute, right? So before I tell you about what we do, I'll tell you what I think we are good at. So over the last half-decade, we've really sort of spent time building what we call as a translational model, right? And we often think of translation when we think about medical research. This idea of being able to take things from the laboratory scale into a clinic. Now, while that sounds wonderful, and it is, and it's changed our lives, the question that we've been pondering is how do you really do this with big systems, right? Think about things like refineries, think about things like cement plants, and the question gets a lot harder. And so, what we really spent time doing is building this translation model, which thinks about systems and systems of systems. And the way we've approached this is to think about how you go from knowledge discovery and creation to bench-scale concepts and landscape analysis, which is typically where universities do lots of work, national labs do lots of work, but to really take those two things and then melt it into what we call as a translation funnel. The translation funnel, which I'll give you an example of, allows us to think about scale-up, allows us to think about value engineering, differently put, making things cheaper, and then going into transform and fabricate real-scale systems that we can use to do technological de-risking in a meaningful way. If things work out, sometimes they do, sometimes they don't, 50-50-ish. We come out on the other side and have prototypes, prototypes of devices, prototypes of systems, prototypes of software that we can then go out and test in the real world in a real setting. If things work out, we'll try and create a company out of it. Now, of course, while the hope is every company turns into Broadcom, I'm not sure that is likely to happen. But I'll tell you a little bit about the companies that we've tried to create, right? Now, I wanted to try and emphasize a couple of things here, right? So when we've thought about these scale-up challenges, when we've thought about these systems of systems, we've really been focused on 3 questions and asking these 3 questions over and over again. Is it scalable? Is it cost-effective? And will it have impact? Now, the reason that this turns out to be important is, these 3 things, effectively making things both cheap and good, is fundamental to what we think is necessary to ensure climate change mitigation at scale. That sort of sets the framing around why carbon management. I also want to point out, I think 2 of the things that we're very proud about. UCLA is the only university in the world to have won an X Prize. We won an X Prize in 2021. We also did win the Livability Challenge in the same year. I want to point out both competitions had about 400 entries from around the world. We were, in both cases, the only university to win. Now, I want to tell you a little bit about why we've sort of been thinking about companies, right? And the company thinking is actually quite important. The company thinking really matters, not because, we're in California and there's a bias for creation and everybody's got a startup on every street corner, but companies allow you to pressure test whether something will really work in the real world. If it does not work in the real world, you can argue that there isn't really a good reason to do it. So we've been thinking about really sort of, ask what is possible, right? So unhindered discovery, but pragmatism towards delivery. Thinking about timelines to impact, right? Because if you're going to take 50 years to mature something, it definitely doesn't belong in a company. And the last question is, how do you think about continuous improvement? So continuous improvement really matters, and being able to distill that into the academic paradigm where you thinking about impact as sort of your metric of success really starts to make a difference. So I want to point out, there's about 5 companies in the portfolio doing all kinds of things, going from cement and concrete decarbonization to hydrogen and carbon removal at scale, which I'll touch on for a second, all the way to thinking about lithium and lithium separations for all of us that drive an electric car. Now, to tell you exactly what ICM does, finally, right? So we really work only on 2 things. We work on carbon dioxide emissions avoidance, removal, and utilization. And we work upon technologies to create new supply chains to produce what we call our energy storage materials. This is all that we do. And the reason that we do this is we think fundamentally industrial translations of industrial processes, think about cement, think about steel, think about hydrogen, and thinking about ways to store and manipulate energy is fundamental to what we need to do to actually deliver climate change mitigation at scale. I don't want to spend a whole lot of time talking about this any further, but I want to give you an example of the types of things that we do, right? So I want to go all the way to the right-hand side of the screen, my right-hand side of the screen. You see a bicompartment cell. For all of us that like the SI system, those 2 containers are about 6 centimeters tall, right? That's an interesting experiment of what we call as electrolysis, running an electrical current through water to be able to use electrons to stimulate a series of reactions. That is work that we started doing in 2019, 2020. In 2023, we scaled that process up approximately 1 million times, built 2 pilot plants, one in Los Angeles, one in Singapore, to demonstrate that this process could be rendered into near industrial scale. The idea of doing this is not to say how big can it get. Indeed, it is to say how big can it get. But the better question is, will it work as it gets bigger, right? So we often work in the academic environment where it's like I say, on a laboratory bench, everything can be made to happen, right? The question is, as it gets bigger, can it still be made to happen is a really important question to ask. And I think what is important about this is it allowed us to prove, in this particular case, focusing on a technology for carbon dioxide extraction from the atmosphere, you could indeed do it. We went from there, and because one challenge is never enough, we decided to take on another one. This is a large demonstration plant that we're building in Singapore, which is funded by the government of Singapore. To give you an indication of scale, those towers that you see on the right-hand side and the left-hand side, they're approximately about 45 feet high. Now, the reason that this matters is it's exactly the same chemistry that you've been following from those little cells into a pilot plant, into a demonstration plant, and going out from here into a plant that's about 30 times larger that gets to full commercial scale. The idea here is really quite simple, right? It's to ask the same question over and over again. Can it get bigger? Does it get cheaper? Does it work as intended? And you need to go through this because you need to build confidence data sets over and over again, right? The confidence data set is actually really important because what we're trying to do, and to try and level set the problem, climate change mitigation is undoubtedly the largest thing that we will ever do. To give you an indication of scale, we as a society emit about 40 billion tons of carbon dioxide per year. For those of us that don't deal in billions of tons, as an example, I want you to consider that all of the cement and concrete that we produce in the world year upon year is only about 25 billion tons, right? So to give you an indication of scale, you need to go 1.5 times larger to be able to think about the scale of CO2 emissions, right? And so when you think about anything that large, obviously it needs to be cheap. So the central framing that I want to offer is what we're trying to do is really make things cheap and good simultaneously. I want to close out with really talking about sort of action themes, right? So I built ICM to be what is known as a focused translational organization. Lots of text on the slides, right? I'm trying to weigh you down. I really want you to sort of focus along on 3 things. It's built with the idea that it's a special purpose organization, right? So it's designed to do things that are not done in national labs, not done in companies, and not done in universities. We want to play in a very specific space where nobody else plays. We're focused really on areas that we think really matter, and so we're really working on things that we think have direct societal benefit. So society is indeed our sort of final audience, and so if you can't deliver an impact to society, we shouldn't be doing it. Last part is ICM was built to be, built with a bias for action and with a mission orientation around it. So we focus, in a very, I would say, a very light horizontal way, with the idea being that you want lots of really quick decision making, and you want really quick translation into delivery, right? And so this idea of trying to build an FTO, I think, is actually quite important, because this allows you to think about how universities can be doing things that really matter in the real world. I want to close out by acknowledging a bunch of really, really good people that have backed us over the years. ICM's got an advisory board, and I want to say this is a board of the best of the best. The best of the best that have been really generous with their time, really generous with their experience, and I think they're really a big part of what has made ICM a success as it is. With that, thank you very much.
Thanks so much, Gaurav. Really clever innovation model around doing hard things. We're going to keep it rolling here. Our next talk is Professor Anya Jones with a focus in aeronautics titled Whether We Fly, Aerodynamics for the Future. The Boeing engineer in me is very fascinated.
Thanks, guys. It's been a great afternoon so far, but we really haven't talked about airplanes enough, have we? I think we can work with the assumption that airplanes are cool, especially when they take off and land safely, right? So once we take off, we have a lot to deal with, right? We have to deal with whatever the atmosphere throws at us, whether you're a wind turbine, kind of dealing with the wind turbine farm wake, you're flying around in a city, or you're dealing with complex terrain, mountains, et cetera. In fact, just the other day, there was a commercial flight in the UK that made an emergency landing with only 6 minutes of fuel left because they spent 2 hours trying to land in high winds. And we would like to avoid that, right? You're getting on a plane, you want to land with a lot of fuel. So one of the things that we're thinking about is how do we deal with landing in complex environments or flying in complex environments? If you're going out into the mountains, into some terrain, you have winds from various things going on out there. And if you're in a plane and you want to go out and you want to land, you want to do a search and rescue, you want to drop off materials, you have to fly around and deal with all of this unsteadiness, right? So you want to land here, but you have to deal with the wind and the atmosphere that's coming off of these objects. And so there are a couple of things that we have to learn to deal with. One is the terrain itself. Two is the wind gusts that form both in the atmosphere and because of these mountains and such. And of course, we want to consider the vehicle performance that we have and what sort of dynamics we're dealing with as we're actually flying. And of course, more and more now we have severe and unusual weather, right? We can't be sure that we're going to have this nice calm weather we've enjoyed to date. We want to move forward and see what we're going to be flying in 10, 20 further. So the question that we ask is, how can we prepare ourselves to fly in new environments and extreme weather? The questions that we're tackling is, how can wind gusts and other flow disturbances affect lift production? So if you get hit by a gust on an airplane, what happens to your airplane? And secondly, how can we sense, mitigate, and predict what's going to happen before it actually hits us? So in my lab, we are taking the approach where we want to understand the fundamental flow physics of these types of problems. We want to model these flows in the laboratory where we have a controlled environment. And ultimately, we want to apply control so that we can reject gusts, right? Imagine if you're in an airplane, the pilot says, oh, we're hitting turbulence, put on your seatbelts, et cetera. And you kind of begrudgingly, put your drink down and put your seatbelt on. What if instead of all that, he could just flip a switch and all of a sudden there is no turbulence to the aircraft? You just reject it. That would make all of our lives that much more comfortable. So we're doing this by building water channels, doing water channel experiments, looking at how flows interact with wings, measuring those flows, and ultimately applying theory to see if we can't figure out the underlying physics of why we get transients and force and why this aircraft bumps around through the atmosphere. And our approach is just to go back to theory. If we have a wing that gets hit with a gust, what happens? Right? As that wing passes through a gust, lift builds up, and there we go. And we get this unsteadiness and this transient in the lift. And we could use equations, we could compute that. But if we have a finite gust, we have bigger problems, right? And everything in the atmosphere is ultimately going to be finite. And in order to compute that, we have a little bit more math, but it turns out that the math actually works pretty well for simple gusts. However, if we have a big gust, if you're flying through a mountain, you get hit near a mountain, and you get hit by an updraft, what happens? Well, as your wing passes through this gust, you get this really big buildup in lift. You get what we call a vortex up here, and that generates this huge transient lift, and we have to figure out how we're going to reject that. We could do some math. The other thing we haven't seen today is equations. We're all engineers, guys. So the force comes from the movement, the change in momentum of the flow. And we can compute that really easily by looking at how the vorticity or this vortex moves around this wing. And if we can control the motion of that vorticity, then we can control the lift and how it's building up on the wing and ultimately how it's knocking our airplane around, right? We could do that doing a bunch of different models, but what turns out to be true is that no matter what model we use, we get a different way to reject that lift, that gust, but we get really similar lift histories. We can reject that disturbance using even really simple models that you could put on board a little autonomous aircraft. And for an ideal gust, that works out really well. But we need to think about how we're going to deal with more complicated gusts. So for a simple model, if our wing is going through a gust, we could use one of these models and we could come up with some optimal kinematics that would allow our wings to maneuver so that we don't feel a gust. Now, granted, in this scenario, if you're riding on this aircraft, you're now diving into your gust, and you might not want to do that either. But we're working on that. So it turns out that by diving into this gust, you generate essentially opposite vorticity that allows you to counteract the vorticity that's in that gust, and ultimately just reject that lift transient. And so now we kind of have a lift that's closer to zero, and your aircraft kind of maintains a steadier lift. We can go through more analysis, but what turns out to be true is that this vorticity that we generate on the wing counteracts that gust. And so we need to not only consider that big blue vortex that you saw in that first video, but all of the little stuff that's floating around. And that's important because the gust itself is vorticity. And so if you're flying around in a mountain, all of a sudden you now need to consider all of this flow that's in that environment, in that atmosphere itself, not just what your wing is creating. So if we want to then fly around in the mountains here, we're dealing with this wind, right? We're dealing with the gust that's coming off of the mountains. But now what happens if we get a storm, right? Now we have a new source of vorticity, a new source of unsteadiness. We still want to be able to go out and fly, right? We still want to rescue somebody out there or land safely. And so how do we consider all these new unknowns? So the questions that we're kind of moving forward and thinking about are, how can we prepare to fly in extreme weather, right? If instead of just a friendly little wake off a mountain, you now have a hurricane that you're flying into, and you want to be able to go through and land safely. The first step is that we're working on looking at ideal gusts, kind of like some of what I just showed you. We want to explore complex disturbances, like something that arises due to weather. And finally, we want to find new ways to sense these flows coming in and reject these flows without having to make a nosedive into it. So with that, thank you very much.
Thank you so much, Professor Jones. And now from airplanes to robots. Professor Dennis Hong is going to be talking about the robot star who couldn't act, but taught us everything. Lessons learned from building Cosmo, the robot of the electric state.
Okay, the robot star who couldn't act but taught us everything. Yes, this is a real title of my talk, and yes, this is a true story. Again, my name is Dennis Hong. I'm a professor in the Mechanical and Aerospace Engineering Department and the director of ROMELA, the Robotics and Mechanisms Laboratory. In our lab, we really create a lot of cutting-edge robots. I actually counted all the robots that we created, and it was 56 different robots. Oh, sorry. Okay, there you go. So I actually counted all the robots that we developed in our lab, and it was actually 56 different robots, from three-leg robots that uses passive dynamics that walks. It was actually inspired by hair braiding. Amoeba robot chemically actuated that everts. A wheel-leg hybrid robot, climbing, jumping, rolling robots, all different shape and sizes and different morphologies. And these are some of the robots that we developed. In terms of humanoid robots, we actually developed 16 unique different type of robots. This robot is called Darwin. You've probably seen this. This is one of the most used research and education humanoid robot. Charlie is considered the United States' very first full-size humanoid robot. Thor RD for the DARPA Robotics Challenge. Sapphire, shipboard autonomous firefighting robot. It's a firefighting robot for Navy ships and many different sizes, different type of robots. you probably know one of our superstar robots. It's called Artemis. Artemis stands for Advanced Robotics Technology for Enhanced Mobility and Improved Stability. So this robot is still one of the most advanced human robots out there. You kick it, shove it, and you cannot make it fall down. And when our students are stressed, this is what we do in the lab. What you see over here is a 5 centimeters tall obstacle, and it's not using perception. This is all reactive control. This is a 5 centimeter sponge, and this is very difficult to do, but absolutely no problem. These are randomly placed objects. And this is the very first running humanoid robot from academia. Running meaning that both feet off the ground. There's a flight phase. And we're very proud of this robot. Let's make it do some useful stuff. What you see over here is a fully autonomous. It's using stereo cameras in the head, and it's identifying obstacles and doing path planning and walking. Right? So let's make it do some useful stuff. This is an empty box, by the way, and it did pretty well, so let's give it a little bit bigger challenge. This is a huge box, and by the way, it's a real-time balancing as it's walking, but it cannot see because the box is covering the eye, so we just put it on the head and everything works okay. All right? And it can push carts. Normally to do this, you have to create a new behavior, but this robot is so robust, we just make it go into the cart and everything works great. So this is Artemis, Advanced Robotics Technology for Enhanced Mobility and Improved Stability. However, in our lab, the acronym is a little bit different. Artemis stands for a robot that exceeds Messi in soccer, because we also make it play a game of soccer. So there are hundreds of different type of robotics competitions. We really like this competition called RoboCup. RoboCup is an international autonomous robot soccer competition where people, researchers from all around the world build humanoid robots, and they actually try to play a game of soccer against each other. So every year, new technology, new robots. It's a great benchmarking event. It's also a conference. So after this, we publish paper and everything. The cool thing about RoboCup is the official goal of RoboCup is by the year 2050, have a team of robots play soccer against the human World Cup champions and win. That's an official goal. So it's very exciting. So let me quickly show you last year's RoboCup. Last year RoboCup was in Eindhoven. So it's 2 against 2. This is Team UCLA, Team USA against the German team, defending champion. We don't have a lot of time, so I'm going to skip some of the things. So all robot was the fastest and the strongest. Look at the speed of that, 2.5 meters per second. By the way, at the time, our robot was the world's fastest walking robot officially. My favorite scene is this. I'm going to check this out. So the German team is about to put a goal, and then Artemis is like, oh, we got to block that, and there's an obstacle. It tries to go around the obstacle. Look at the head. It's looking around, searching for the ball, and fantastic. It doesn't end there, and then looks around. Oh, this is an opportunity, and it just runs to the other side. Look at its head, looking around where the opponents are, where the goal is, and it tries to kick the ball into the goal. And can you do it? Yes. Okay, that's fine. And the rest said, okay, I can't do it. You take over, and the second robot automatically takes over, and the second unit, Artemis, comes and it's actually very exciting in person. Finish it. And yes, to the corner. Isn't that cool? So at this point, the current score I think was 6-1. And with this, we became the world champions in RoboCup, Team UCLA, Team USA, right? And I am so proud of all of our students, hardworking students. You know, I get tears in my eyes whenever I see this. Yeah, if we win, they automatically graduate, so I have to sign all the paperwork. Anyway, so this is Artemis, and this is actually our 6th time winning RoboCup. This is a big deal. We have a lot of fans, by the way. Mr. Bill Gates is a fan. He actually came and if you look at Artemis, he actually signed the thigh of the robot. And everyone knows Gates Notes, right? Last year, Gates Notes was us. We are featured on Gate Notes. Anyway, so that was a very exciting robot. It's an athlete robot. However, today I want to talk about something different. It's not an athletical robot, but it's actually a movie star robot. So I was actually a professor at Virginia Tech for 11 years, and 11 years ago, I moved to UCLA. UCLA, Los Angeles, we have Hollywood. By the way, I decided to become a roboticist by watching Star Wars, so science fiction is really dear to my heart. So the past 10 years, I really tried to connect the film industry, robotics industry, and believe me, I really met famous directors, producers, casting directors, and I showed them our robot. By the way, probably you know Denis Villeneuve, Dune director. Any no Star Wars fans? No? Oh, okay. Oh, yeah, there you go, right? I met a lot of directors and people like this. Mark Hamill is not a director, but Luke Skywalker, he's my child hero. Luke Skywalker. So they come to our lab. I show them our robots walking, climbing, jumping robots. And everybody says, wow, Dr. Hong, this is fantastic. And then I propose some projects, and everybody says, no. 100% decline. They say, in our industry, we don't need robots. We have green screen, we have computer graphics, and 100% everything got canceled. However, I didn't give up. 2 years ago, I met the Russo brothers. In case you don't know the Russo brothers, they did the Avengers Infinity War, Avengers Endgame, one of the hottest movie directors. Same thing. I show them our robots. They love it. But, oh, Dr. Hong, haven't you seen the Avengers? It's all computer graphics. Isn't that cool? So what I said is, okay, use computer graphics for the movies, but when the movie comes out, at the premiere, at the red carpet, how cool would it be if a robot in the movie actually comes out and greets people? They loved it, so we started this project. At the time, they were directing a movie called The Electric State. Millie Bobby Brown, Chris Pratt, a lot of A-star, superstar people as a big movie. It's actually the biggest budget movie in the history of Netflix. So I'm not going to give any spoilers, but this is the main character. It's called Kid Cosmo. It has a big yellow head. So we started this project. So Kid Cosmo looks like this. Great design as a character. It's a beautiful robot. It's cute. But in a real engineering system, this is a horrible design. Big head. When it walks, it goes like this. Whoa, loses balance. Huge boots, collision, the center of gravity, momentary. This is all out of whack. You should never design a real robot like this. You should design a robot like this. Artemis is designed, so everything, we all know, it needs to obey the rules of physics. There's a reason why the length ratio, the moment of inertia, center of gravity, everything is optimized for high performance. And this is how you should design a robot. Okay, so our research question before was, how do you design a robot for high performance? But now the question is the opposite. How do you make a horrible design robot to perform very well? So you're running out of time, so I'm going to skip a lot of things. By the way, it's all on YouTube, so you can check it out. A lot of interesting challenges. In this case, the character, the shape, and the dimension was given to us. How do you package all the actuators, all the power and electronic sensors into a small body? How do you make it walk? But again, it was a huge success. The Russo brothers absolutely loved our robot. So some of the interesting other questions is, the robots that we normally create, it needs to pick up something, it needs to walk, it needs to do some task. But in this case, the task is acting. What is acting? How do you portray emotion by motion? Emotion by motion. How do you capture the actor's look and feel? How do you quantify that? Very, very interesting, different type of problems. But again, I'm going to skip all this. I'm getting red flags. But yes, so again, it's cute. It does some interesting manipulation stuff. And Everly absolutely loves the robot. All right, so interestingly, so probably you all know we talked about AI, different approaches. Our lab, we divided our lab to Team A and Team B. We made 2 identical Cosmo robots. Team A is using a model-based approach. In other words, we engineers for the past 100 years, we have a mechanical system. We use the rules of physics, use mathematics to model it, and we do control. That's the traditional way. We use MPC control. So Team A is doing model-based. Team B, which is the relatively new approach, a data-driven approach. In our case, we're using reinforcement learning. So we have 2 teams in our lab competing with 2 identical robots, 2 completely different approaches, different philosophies. So we get simulation, and then from the data, we train it. At this point, this is the MPC-based robot. It's starting to walk first. So it's taking its first baby steps. Okay, so model-based versus learning-based. Who will win? Who won? Actually, the movie actually flopped. It's actually a fun movie, by the way. It's a fun movie, so go and watch it. It's on Netflix. The movie flopped, but the research did not. This Cosmo gave us a challenge. It gave us a brand new, different set of different research questions. So again, a failure in one domain sometimes can inspire different research to a success. So this is the true story of Kid Cosmo. Okay, I'm out of time. Thank you very much. Thanks.
Okay, how anybody can top Dennis, right? Thank you very much for everyone. As you can see throughout today, we do a lot of exciting research here. And you can see from videos and everything else that all our students are deeply embedded in all the activities we do. So this is really exciting time for us. But I also have a distinct pleasure to introduce our UCLA's Chancellor, Julio Frank. He officially assumed his role January 1st, right, 2025, just not even 10 months ago, my goodness. And a lot happened. And through it all, he's been really fearless leader for all of us. And his support for engineering school has been tremendous. He's also a distinguished professor in the Department of Health Policy and Management within the UCLA Fielding School of Public Health. Chancellor Frank is a globally recognized leader in health research and has served in top leadership roles across both government and academia in the United States and Mexico. Before joining UCLA, Julio served as the president of the University of Miami from 2015 until 2024, and as the dean of the Harvard T.H. Chan School of Public Health from 2009 to 2015. As Federal Secretary of Health of Mexico from 2000 to 2006, he implemented a groundbreaking program that expanded access to healthcare to over 55 million uninsured individuals. His impact is tremendous. He was the founding director general of Mexico's National Institute of Public Health, and has held the senior roles at the World Health Organization and Bill and Melinda Gates Foundation. Chancellor Frank earned his medical degree from the National University of Mexico, as well as a Master of Public Health and joint PhD in Medical Care Organization and Sociology from the University of Michigan. I also want to point out that we also have the Chancellor Frank's Associate of the Chancellor, Dr. Felicia Marie Nowell, joining us today. She's also a distinguished professor of medicine here at UCLA. Julio, please join us on the podium. Thank you so much. Thank you so much for coming. Thank you.
Thank you. I went Cosmo here. I don't know about you. That was really, really fun. I'm in awe, and thank you, because sometimes the job that I do is a little bit stressful. And when one gets to see the incredible amount of talent that we have at this extraordinary university that I'm still discovering, because yes, I've been here less than 10 months, I just feel energized, and I know that anything we can do is worth the effort if it leads to the expressions of talent and impact that we just saw in these 3 Bruin talks, just a small sample of everything that happens here at our Samueli Engineering School of Engineering. I'm also in awe of engineers. As someone in a very different space of human activity, I can't help admire the ability to think something and then actually see it concretize in an object and in a solution. So I'm going to start a practice of hugging an engineer every day. I know you've had a really extraordinary day. It's an extraordinary day at an extraordinary school. And it is an extraordinary day because we're celebrating 80 years of milestones for UCLA Engineering. And this also marks 25 years as the UCLA Henry Samueli School of Engineering and Applied Science. So I first want to acknowledge a true Bruin, probably the one who started that trend that we heard about being a triple Bruin to do anything important in life. Henry Samueli, who's here, who earned his 3 degrees here, who got his start as a professor here and And we just honored one of his alumni, one of his mentees, and began his pioneering company, Broadcom, here, which I was also impressed to hear just the way that company has taken off. Henry, thanks to your legacy, UCLA continues to lead the world in semiconductor research and education, and it just sets an inspiring example for Bruin's present and future. So I can't thank you enough. You and your wife, Susan, have created opportunities for generations of engineers and have inspired their careers. When you spoke at the engineering commencement earlier this year, you told to our students, and I'm quoting, "Technology is transforming almost every industry at an ever more rapid pace. So stay knowledgeable, never stop learning." And I can't agree more. We have launched this idea of UCLA for life. Education is not something that happens in a defined period of our lives. It is a lifelong journey, and we want to make UCLA the provider of evolving educational services as people from every corner of our society embark in their professional life journeys, accompanying them at every step of the way. I also want to take a minute, and I'm going to be brief because I know there's a reception and many other things coming up, but I do want to acknowledge very much Alisa Park. I met you very early, and you had just started, and I had heard wonderful things about you, but once I got to meet you, everything that I was told was small compared to what I've seen you realize and the way you lead this school. You inspire our 7,000 engineering and computer science students to go out and change the world. So thank you for your leadership. UCLA Engineering, there's much to celebrate since it opened its doors in 1945. Since then, our engineers have made breakthroughs in fields from clean energy to nanotechnology. In the 1950s, they figured out how to get clean water from dirty, unusable water by inventing the first reverse osmosis filter. Today, this, by the way, is the dominant technology used to desalinate water and provide clean water to millions of people in places where it is precious. It's a lifeline around the world. Another great moment in the history happened on Bolter Hall, only 350 yards away. Professor Leonard Kleinrock, who I understand is here, and he sent the first electronic message across ARPANET. This led to the internet 56 years ago this month, 56 years ago. So imagine that, a communication revolution that began right here in Westwood and now connects the world. And since then, I mean, we could spend the afternoon enumerating the contributions, and we just saw 3 outstanding contemporary examples. And the interesting thing is it will keep going. Every time that anyone questions the value of universities, we need to keep reminding them. We need to show them the incredible amount of prosperity, security, improved health, improved longevity, innovation in every field that universities have generated for society. Today, our students are working with faculty and staff to shape everything from AI and machine learning to biomedicine and digital health. UCLA Samueli School of Engineering will drive us forward as a leader in technological innovation. And that's exactly as was mentioned in one of the awards, because universities expand the frontiers of knowledge. Good universities expand, but don't stop there. They seek to translate that expansion in the creation of new knowledge into solutions for the very real problems and most complex problems facing humankind. We've launched in our strategy what we're calling the UCLA Research and Innovation Blueprint, a new blueprint. The existing blueprint for the last 80 years, coinciding with the founding of this school that was entered into that came just out of World War II, is being challenged, and I think we're seeing the end of that. We need to design and implement a new blueprint to keep the motor of science and innovation alive. And we're determined to do that from here by enhancing our partnership with industry, with investors, with philanthropy, and continue for sure to rely on federal and state funding, but diversifying our sources of financing. UCLA, Samuel is working with the UCLA College of Physical Science, for example, to start a quantum innovation hub, following this, this model. We are developing our UCLA Research Park as a way in which we hope to innovate the way we innovate. And Elise is chairing a university-wide task force on private sector partnerships to continue to drive the funding of that duality, expanding the frontiers of knowledge and figuring out ways to translate that knowledge into solutions. So I'll finish with another quote from Henry from his recent speech. He said, "Passion is what gives meaning to our lives. It's what allows us to achieve success beyond our wildest imagination." He's again right. Passion has propelled our school to new heights, and it will continue to do so. Congratulations to the UCLA Samueli School of Engineering for 80 impactful, exemplary, and connective years. Thank you very much.
Thank you so much, Chancellor Frank. I'm always such a fan of your eloquence and your presence. Well, folks, that brings us to the end of the program, and what an incredible program indeed. I had a couple recaps. One is, Chancellor's going to hug an engineer every day. That's number one. Number two, no matter how our sports teams do, remember, we're the Alabama of world robotic soccer. But in all seriousness, if today wasn't a day that inspires all of us, I don't know what is. This is a very special place, and we are all connected and bounded by this very special place. So hopefully this re-energizes you, this re-engages you to be more active and more passionate about your UCLA. And so just two logistical items. First, we have a great catered reception at the Bolter Courtyard, open to everyone, so excited to see you all there. We're going to have some really notable student tours, and we're going to be recognizing our student awardees at that event. So please stick around, be there, great food, great conversation. And then number two, would ask all of the awardees to come up on stage to take a photo with the Chancellor, with the Dean, with Henry, and others. So folks, great evening. Thank you so much for taking time out of your Saturday to represent UCLA. And as always, go Bruins.